basic fundamental physics. So what I will try to explain to you is why it is important. And as I mentioned, the Astro AAPM uh, course revision 2023, that was after 7 or 8 years they came in the revised course. They look at what is the training needs of residents who are today, and they also look at after 20 years, 30 years, so many things would change. So what is required for you to have training as a radiation oncologist? That is very important. And so it will be a series of lectures. Astro APM course we will cover entirely for physics. For radiobiology, as I mentioned, with Jain, we will do the Royal College of Radiologists course as syllabus plus HBNI, Homi Bhabha National Institute, to which we are affiliated, Health Science PhD program. So this is for tomorrow. In the beginning, 1.5 hour, very basic aspects of genes and genetics. We will not get into details. And then radiobiology, the primer, first for few hours, 4 hours of radiobiology, so that you understand the basic concept upon which you can build for future and advancements. So this is what I was talking about, the revised core physics curriculum. We will cover this all. This is a paper in Red Journal. You all should see. In this, they have 56 hours of didactic lectures. So what is written here against each topic, like orientation, fundamental physics, atomic, nuclear, and in the bracket, what we have written, what we will cover in our this thing. Plus, rest of it will be through discussions, practicals, and assignments. So that you go through it, and I try to see that if we can remove some of those things, but I can't really remove anything, because each and everything that is there in this core curriculum, it is actually essential. If you do not know any of these things, later on when you practice as radiation oncologist, it will be important. What is important to see is how much of time they have given to imaging fundamentals. 5 lecture hours. We will reduce it to 3 hours. I have to request all the faculty to agree. No one would say no for teaching students. When we were residents training, that time we had just moved away from radiology. Before that, my seniors, my teachers, they were from a unified department of radiology. What they used to do, imaging also, and also used to give radiotherapy. Actually, the name of ASTRO itself is American Society for Therapeutic Radiation Oncology. That means that therapeutic versus diagnostic. The Royal College of Radiologists, it is called Royal College of Radiologists. It has a faculty of clinical oncology, to which I belong, and faculty of clinical radiology. So today, now we have realized that imaging is so important. Similarly, many things that we will study, you may not think that is very important, but in a period of time, you might realize it is very important, without which you can't have concepts that are required for practice, not for giving an exam. Exam, of course, everyone will pass, but I'm talking about for practice. So in the first lecture is fundamental physics, atomic and nuclear structure, production of X-ray, kV X-ray, kilovoltage voltage X-ray. I'm not talking about LINAC. And this is the first section, 3 sections of Astro APM. I will cover in 35 to 40 minutes. So this, imagine a young radiation oncologist, okay, who has joined the department. I am becoming a radiation oncologist who will treat cancer patients using radiation plans made by the physicist, executed by technologists on very safe modern linacs. Why do I have to get into all this, so many things? If you give an idea, when I bought my home, I didn't have to learn civil engineering. I bought my home, I moved into it. Of course, I spoke to the architect, got things done. When I bought my car, I didn't have to learn automobile engineering. I drive it well. I enjoy driving my car. I love my car. Okay. So I'm now becoming a radiation oncologist. But when I decided to do home cooking, then I had to learn many things. And when I decided to become an artist, painting nature and its creatures, then I had to learn so many. So some things are completely standardized. They will be used in only a particular way. They're standard. Nothing else can be done. Whereas cooking or doing an art, there's so many permutations, combinations, so many things you have to understand. How you combine, when you combine, what comes out, it matters a lot. Okay. So that is what now I'm talking about. So I'll take the last example of becoming an artist. So imagine all of you, budding radiation oncologists or practicing radiation oncologists who already are practicing, you all are artists. You can say, how are we artists? So This picture everyone knows, Mona Lisa. Everyone knows this is in the museum in France. So the beauty and intensity of this painting obviously is self-evident. No one ever would say, I don't like Mona Lisa. There's something, some charm in there. When you go to the museum, everyone will stand there, for some time. And for wherever you look, she will be looking at you. So radiation oncologists have to master the use of ionizing radiation to paint colors and lines of required doses and intensity on the canvas of tumor without spoiling normal organs, and all inside the frail frame of human. See, all our patients are not frail, some of them are very fit, but no matter if you may be the strongest athlete, if 100 gray of radiation is absorbed in certain parts, you are gone. So every human organ and body is frail to a dose of radiation which is not safe for that organ or for the. Okay. So, and how we can do that harm if we do not know how to use it. And it's not only just because of technical fault or something, the fields were not there, it's because of our lack of understanding of the concept as to what is happening, where it should be prescribed, what happens with different normalization, etc. etc. So I will come to that later. So this is just for you to remember. Remember, you are the artist. And actually, artist is, of course, you're right now, you all just draw lines, contours. Okay. There is life beyond contours. This is one area where AI will certainly take over the top of contours. I feel so bad, really. I mean, the worst thing I feel about residents is when so much of their time goes in contouring, which is the most useless job, but someone has to do it. And this is a job which will go away completely. This is the lowest hanging fruit for AI or machine learning. I mean, just figure out, just contour. Normal organs, obviously, and over a period of time, even tumor contouring or all those things, they will do the lymph node regions and all, they will do better. But so then but you will still be an artist. So I've shown this picture. I don't know from where I got this picture. This is an old man. He's a painter. He's painting. You can on the wall. He has some rustic sort of themes. He has put it nature, etc. A lot of paint, small, big ones, different sort of brushes he's using. So an artist can make a beautiful original creation only if he or she has a good knowledge and feel of the two things they need to know. One is the canvas, its type and texture. There are so many different types of canvas. People all paint on a wall, on a canvas or paper or wherever it is, and the colors, its shades, types, and appeal. How they look, and the coloring instruments like the brush. One is brush or the brush or whatever they want to use, or with nails, whatever they use. And that person can conceptualize, imagine, and foresee the finished work. Okay. Finally, when you started, it is just a blank canvas or a blank wall, something. But when you finish it, then you have to have some idea as to how it will look. And this person also respects the critics, that okay, it should have been there. So at least you don't have to follow them, but at least understand. So now putting it in our context. So canvas and its types and textures. We'll focus on what is a canvas in terms of, imagine all of you are great artists painting something beautiful. Okay. So what are the canvas types and structures? So one is simple thing is anatomy, because like if you just a simple physical thing is what you see, the Gray's anatomy, different planes and different parts of the body that you see. This is the anatomy, which is a canvas, and that's what we do in contouring all the time. You draw body, you draw skin, you draw lung, you draw everything. Okay. And then there's a canvas also, internal canvas. Okay. Canvas that you don't see the internal property, which is the different parts, the surface and the shape, the plane and the relationship, the bone inside, the calcium, it has metal. Sorry, the slide is not seen properly. And where is the air, where is the density of the water, the motions, rhythms, and changes. And there are many things which are not seen. So when you make your contours, GTV, CTV, PTV, etc. You take all these things into account, which is also your canvas. not only the types, but the texture. I think what JP was also mentioning about the texture. So the canvas is also the tumor, because ultimately you want to paint the dose on the tumor. It so happens that around the tumor there are normal tissues, but essentially it is a tumor. So tumors also comes in various sizes and shapes. Their relationship with other normal tissue, they also move, they change shape. They are unseen parts of tumor, what we call subclinical disease. They have a potential to double, to invade and spread. Each tumor has a different biology and responsiveness. They have stem cells, stroma, and heterogeneity. So, I mean, it's already coming in where you're using biological dose painting, not just taking into account the morphology. Right now, it is very simple term. You just look at the FDG uptake or uptake of some other radionuclide, which tells you about the biological activity. But it will be much more what we call the era will come of molecular targeted radiotherapy, when it will be based on the particular molecular changes that you would target. Tumor is not homogeneous neither at the gross level nor at the microscopic. So this is a wall painting, wall art, and this is on the house where Kongen had lived, must be in his childhood. I don't know which year he was born, 1895. Of course, he came out with his X-rays. He must be a young man, and that was in Utrecht he lived. And this shows two things. Of course, Ronjan with his beard and his typical face, and the hand. All of you know, if you don't know, the hand is said to be his wife Bertha's hand. You know, the X-ray, first X-ray he took to the hand, and a ring was seen, and she said that she was very scared. You know, like seeing skeleton was like seeing your death. Okay, so that is what it is. But so this is how X-rays. So the end of 19th century, and I will at around the same time, this lady, wonderful lady and scientist, Madame Curie, she was working. She was Polish, and she came to in Poland. They were not allowing women to study beyond a certain level. That's why she came to France in Paris, and there she met her guide. Later on, became her her husband, and she amount of work she did, if you study her the notebooks and the work she did, extensive work she did, and then she found radium. And another metal she discovered was polonium. She named that in the memory of her motherland, even though her motherland did not allow women in those days to study that much, but that's your motherland. And she is the only person who won two Nobel Prizes, both in physics and chemistry. And her family, she, her husband, her daughter, and her son-in-law all got Nobel Prizes. Okay, so many things. So she is an inspiration. I think will always be an inspiration for everyone, not just those who are in radiation sciences or use radioactivity, but for everyone. So so Curie pavilion is there in name of Madame Curie in when research in chemistry and physics, and there's a Pasteur pavilion which is in Claude Regor. Regor, you may not have heard the name because the very old in text it was there, but a lot of research in biology and medicine was happened, and this was a radium institute which was established in 1912. So very early on they were looking at all these things, and then very soon in the next 20, 30 years, all the major European cities and some American cities had a radium hospital or radium center. Before that, treatment of cancer was so difficult. Imagine those were only 50 kV X-rays, 90 kV X-rays, the tubes will just go fat, they will heat up and everything else. So this was a new revolutionary treatment for well-selected cases. Actually, it could cure some cervical cancer, it could cure some oral cancer if they were very early, which was not really happening. So that's why the institutions were named in this thing. And I'm told in India also there is a radium road in Ranchi or somewhere, some radium must have come to some hospital. So that is how it was. So Radium Institute in Paris, the biology of Curie therapy, and in the Radium Institute, Manchester, which is very famous in Christie. So there are a lot of dosimetry of Curie therapy. And Patterson not only did all this, your point and all, but of clinical radiotherapy as to what should be the dose fractionation, what should be the volume, when it is curative, when it is palliative. So all those distinctions and the Patterson-Parker system of brachytherapy. So in India, Tata Hospital was established in 1942. So it is more than 80 years ago. And we were one of the first centers to have a radon plant, radioactive radon. So they were sort of sealed and they could put it for brachytherapy. Okay. Of course, later on, it was abandoned because of the hazards of associated with the radon gas, which is leaked. But this is history. So what do we do and how this is done in radiotherapy? And that's how we will come. So before that, so we give energetic radiation. Give means absorb. And the dose is absorbed. That means this deposits lethal energy in the tumor. This lethal energy kills the cells by damaging the DNA, and it doesn't know whether it's normal cell or tumor cell, wherever there's enough energy radiation. And when we give radiation to the tumor, it has to traverse through normal tissues, and that's where it causes the biological side effects or damage to healthy organs, because it just doesn't go directly immediately to the tumor. Even for that matter, even proton just doesn't come up only in the tumor and absent before and after that. And brachytherapy also, the rays will not stop just when the tumor is over, even though inverse square law is. So how to reduce the toxicity side effect is, one is by reducing the radiation dose to the normal tissue. And that's where you need to understand that how we will choose the physical properties of a beam, and on top of it use technology to shape and modulate the beam. Sometimes in modern times, people think only it's the technology, because you have this linac, they have this gadget, they have these features. Just with the help of technology. Technology is one thing, but the property of the beam is also very important. So the beam, radiation beam is the color, and the technology linac is your coloring instrument. Okay? You may have the best paint brush with you, but if the paint itself or the color that you use is not good, you will never be able to create that. Okay? And so a good artist will know that this is the right, painting material, and this is the correct, brush, and of course this is the correct canvas. And of course, we can also be kind to the normal tissues by fractionating the dose, which is safe and acceptable for that kind of thing. So give and take. I just use the cover page of this. So, I mean, everyone knows this, but intuitively we don't get it. So radiation oncologists, we give radiation. We are interested only in the absorbed dose mainly. But of course, exit dose, we would want no exit dose, but some exit dose comes, and that time it is also used for imaging on the machine. Otherwise, we are not in, or exit dosimetry. Otherwise, we are not interested in exit dose, but it exists. Okay? Even in proton, it's not that zero exit dose. Whereas radiologists, they take scans or X-ray scans, they are mainly interested in the exit dose. And ideally, they would want no absorbed dose, but without some dose absorbed, they would only want scattered dose, but some dose is absorbed. In terms of radiation safety, that is important. So they are interested. So give and take, we give radiation, they take X-ray. That is the difference between radiotherapy and radiology. So understand how this ionizing, we're talking of ionizing radiation, it is produced and interacts with matter. We need to understand not just molecules, but the atoms and subatomic particles that make tumors, body, X-ray target, radioactive element, because everything is made up of atoms. What are the universal forces? Okay, universal forces is not just, we don't know electromagnetic this thing, but gravitational, electromagnetic, strong and weak nuclear forces. A lot of radioactivity and interactions are guided by that. We sometimes do not sort of understand that what guides radioactivity. Then the atomic model. Without the atomic model, you will not understand the structure. Both the Bohr's, Niels Bohr's, and then the quantum physics, Einstein and Rutherford, others came. Periodic table, the chemistry and physics of different types of biological and non-biological material. Just because we are doctors, we can't ignore non-biological materials. They also have an importance. And then finally, the three type of mainly effects, interactions, photon, photoelectric, Compton, and pair production. So the Bohr's atomic model. So, initially it was just that it's a cloud of electrons in different shells. So, this electrons are around the nucleus. Nucleus is composed of neutrons and protons, except the hydrogen ion, which only has a proton, hydrogen atom. And they are in different shells. I will talk about it. Each shell has a different energy. So, K, L, M, N shells. So a little bit about these forces. Okay, some of us have not read that much physics, or we have forgotten the physics. So electromagnetic force has also infinite range, but it is much stronger than gravity. Normally, we think gravity is very strong. If you fall from second floor, it's just the gravity which basically hits you. But the other forces are stronger. Okay. Then the weak and strong force. Why I'm mentioning this, because sometimes you feel the weak force, nuclear force, because it's weak, it is weak. It is not weak, but it acts at a very short range. And this dominates when you're talking of subatomic particles. Okay. When people study nuclear physics, so they are studying, basically the focus is what is happening inside it. A lot of things are decided what is happening inside the nucleus. And the weak force is much stronger than gravity, but it is weakest of the other two forces. It is weaker than the strong force and this. And how all these forces come about, the universal forces. So this is because of some force carrier particles, and there's a broader group what we call as bosons. Okay, so they allow all these things to happen. Otherwise, just imagine how, when you have talked about radioactive decay, neutron becomes proton plus electron, or how can proton take in electrons. So it is not as simple as that. Okay, so, and particles of matter, they transfer, when you talk of photons, okay, they transfer discrete amount of energy by, and how this energy is contained in the bosons with each other, and they have their own, each particle will have its own boson. So strong force has a gluon. Electromagnetic force that we deal with is carried by the photon, and then for the weak force there is W and Z bosons. And they say for the gravity also there is a graviton. Okay, the CERN, of course, you have the Large Hadron Collider. If any one of you ever goes to Geneva, please visit this Large Hadron Collider. It is a place to see. I've been there one. Half a day is, you feel less than half a day. You don't able to see everything. So periodic table that we studied when we were in school and for the exams, and you can't remember everything. Uh, of course, we know that there are metals, alkali metals, earth metals, transition metals, and then non-metals and noble gases. You all know noble gases, they don't interact and they're metals. And what is important for us to remember, especially in radiation sciences, is that there is radioactive rare earths, rare earths and radioactive rare earths. So they are lanthanide series and actinide series. Lanthanide, the first one element here is lanthanium, here the first one is actinium, lanthanum and actinium. Okay, so these are arrayed. They are rows and periods, and they are in different blocks, SPDF blocks. We won't go into the details of this, and they are based on the spectroscopic lines of associated orbitals. So different orbitals have different spectroscopic lines. We will talk about the characteristic radiation and this thing and how they are filled. This is a German word, Aufbau principle, which is building up, and the first the lower energy levels and the higher energy, and there's a method how the energy levels are given, and I've already said, for us in radiation sciences, the F block, which is the lanthanide or actinide series, are more important. But many of the heavy metals with a high Z material, because a lot of like the targets, the filament, the shielding, they are all made up of high Z material. So we have to understand what are the high Z material and what are the features it changes when they are high Z material. Okay. So electromagnetic radiation, again, this is a very simplistic way which shows, so everything is, from radio waves to gamma rays. Okay. Here, X-rays have been shown before gamma rays, if you look at it, but that's because, X-rays are a range. You can have only 10 kV X-ray, or you could have, 2000 kV X-ray. Okay. So gamma rays also depend what source they are emitting from. And we know the visible light, which has the visible light, and from radio wave to gamma wave, and the visible light from infrared is on this side and to ultraviolet. So which has more energy, infrared or ultraviolet? People sometimes, ultraviolet rays are harmful. Okay. Whereas infrared waves people use in thermal imaging, and even if you look at in when earlier days we used to go to the dark room, or people used to develop their photographs manually or X-rays, there used to be a red color bulb in that room because it gives you some light. Human eyes can see even in the red light some things, but it has less energy for the photographic film to be exposed. So all cultures always have worship energy in different forms, sun god, all of them. So, all forms. So in Egypt it was Ra, in India it was Surya, and, other places they are different, Greeks and Apollo. So we, as radiation oncologists, we are the modern, peaceful, ionizing energy worship. Okay. No one uses ionizing energy as much as we use. We live by ionizing. Okay. Radiologists, for them, ionizing energy is just one part of it for X-rays and CT scan. Okay. Rest of it is not ionizing energy. Whereas for us, our day starts with using ionizing energy and ends with using it. So we are the modern, and that's the best possible use of ionizing energy to cure a cancer. Imagine. So, coming briefly about electromagnetic radiation. So, there is a dual nature, wave theory and quantum theory. Okay. So, wave theory explains the diffraction and interference, and the quantum theory explains the photoelectric effect and Raman effect. I will talk about it later. Most important, they all travel in straight line in space, and because they travel in space in straight line, geometry is very intuitive, not a very advanced level geometry, a lot of geometry or geometrical shapes and how relation, very intuitive sometimes, basic simple geometry. So you can use that geometric principles in understanding many things, because all the beams are traveling in straight line. They don't just sort of go for a walk here and there. Once they start, they will go straight. Okay. And they all travel with the same speed, which is the speed of the light, which is 10 to 10 raised to the power 10 centimeter per second. And if you remember, there were force carriers, so photons, electromagnetic waves of photons as the charge carrier particles. So this, they transfer energy in quanta, in packets of energy discrete, where it is given by E is equal to h mu. H is the Planck's constant. In the beginning, Rutherford, Max Planck, Einstein, they all work towards what we understand the modern quantum theory. Because there are others also who sort of contributed to that, but that is how modern quantum theory came up. And again, I am saying this, when they pass through matter, their intensity is reduced. We will discuss it later in the next class through attenuation, absorption, and scattering. So this is a depiction. So there are two fields, as the name itself suggests, electric and magnetic field, and they are perpendicular to each other. And it is important that they have sinusoidal variation. So it goes up and down, and for both electric and magnetic field. And in the process, so for any electromagnetic field, there are two important things, which is the wavelength and the frequency, and also amplitude. So we will come later when we talk about the energy. You will see this coming up later. So Einstein is more famous, of course, how he looked. Everyone remembers Einstein because a very distinctive look. This is his picture when he was quite old. Young Einstein picture, people find this old Einstein picture more attractive. I think his hairs and everything else. Yet he was a celebrity scientist. Okay? But he was a true scientist, not just celebrity. E is equal to MC squared whenever you see on mugs, on t-shirts. Because very intuitive. Energy and mass, that you can convert mass into speed of light square is equal to this much energy. That is also happens when you saw radioactive decay. But actually, his first claim to fame was not because of this. Anyone knows what was his, why he got Nobel Prize? Photoelectric effect. Yes. So what has happened, if suppose you say photons, okay, that means you have electromagnetic radiation, all photons are electromagnetic radiation. So that can sometimes emit an electron. So you just put more and more, keep on the intensity of this. You shine the light on it whole day, or put 100 torches or whatever else, but no electron is coming. But only when you use a higher frequency, that means higher frequency, then you will start getting the photoelectric effect. Okay? Then the electrons are emitted. So that shows it is the frequency. That means there is something in the energy of the photon that will only excite or an electron to come out. Just the amount of the photon or light, how much you give the light, it doesn't matter. Okay? So that is, if you remember the spectrum, electromagnetic spectrum. So this was the first sort of principle which he showed. So the Nobel Prize he got was not just for this, but for his this thing to theoretical physics and photoelectric effect. Because a lot of things which he had shown, theory of relativity, could not be proven. Many of the things that he had shown later on, the proof of concept came. So in the Nobel committee feels that if they gave a Nobel Prize for something later on, it should not be refutable. This is not true or something else. So they wanted validation of that. So, but they understood that it is whatever he was saying was very important. That is how the Nobel Prize was in for his contribution to theoretical physics and photoelectric. So inverse square law for electromagnetic radiation. This is sometimes, formula I is equal to E upon 4 pi d square, or just simple, inversely proportional to the distance. So how does this come? And that is the very important, you sometimes forget the formula. It is isotropic radiation. From one point, radiation is emitted equally of equal intensity in all directions. So whatever it was amount, this place like you have simple. If it was 1 unit here, by the time it is the distance is doubled, it has become 4 units, and by the time the distance is 3 times, it has become 9. Because the same amount is there to be spread over. It's not that somewhere else, because the point of start of the radiation or the energy is only here, nowhere else. It is being distributed all over. Okay, so it is because of the sphere. Okay, and remember here we call it d. D is not the diameter. D here is the radius. We're talking about d. Otherwise, sometimes you say d is for diameter and r is for radius. Here d is actually the radius. Okay, radius because we're talking of a circle. It's a distance from there. It's a circle. So this is very important, and inverse square law is not only for brachytherapy, even in teletherapy. I will show you some places and we'll talk about dependence of certain things. So the inverse square law is most important. In shielding, of course, it is very important. In brachytherapy, how the dose falls off and conformality. And even in terms of in external beam, how the percentage depth dose varies with the SSD. Just someone please check. It is coming on the YouTube now. Okay. So now, of course, all of us have to remember some important boring concepts or so what is the atomic mass unit? Basically, it is 1/12. They have taken a carbon atom, which is neutral carbon atom, 1/12 of that as one atomic mass unit. And if you see proton and neutron, they are slightly higher than this thing. An electron is much lighter, about one um, uh, by 2000 or 1200. I'm forgetting now, but it is much lighter. Okay. Then the term like that you will hear electron volt, keV, MeV. So what is 1 electron volt? Is the kinetic energy which is acquired by one electron. If it goes through volt potential difference. 1 electron, 1 volt potential difference. Okay, and that denotes a certain amount of energy which is 1.6 into 10 to the power minus 19 joules of energy. And when you have 1,000 electrons, it just operates like that. 1,000, 1 keV, 1 million is 1 MeV. And most of the times we talk of keV or MeV. We seldom deal with electrons energy, which is less than keV or MeV. So for therapy purpose, it is mega voltage, almost always in MeV. For diagnostic purposes, it is often in keV. And this is the electronic charge. Sometimes this electronic charge is important to know when you talk of dosimetry and other aspects. The electronic charge, you have to understand how much the charge is being collected. That is important. So here there are two metals, copper and tungsten. So the atomic number is different. Copper is Z of 29, tungsten is 74. And if you look at the energy, binding energy, in copper, K is 9 keV, and in tungsten, it is 69 keV, so much higher. And in L shell here, it is only 1.1, it is 11.11. So just because all that has changed is the number of protons, and along with number of protons, neutrons also change. It's not a linear relationship. We will come when we were in school, we studied for each proton there will be one neutron. Okay, but it's not like that as the atomic number increases. And this is what will happen when the the electron jumps down. What happens, the amount of energy which is released. So that will depend upon the difference in the binding energy of different shells. So spectrum, we are talking of spectrum of radiation. First I showed that. So which is basically how different parts of a series are arranged. And we're talking of energy, or energy is also same as wavelength. So if you look at, these are the different wavelengths expressed here in Armstrong. And this is a visible light. If you see, this is beyond this is ultraviolet, and beyond this point it is infrared, and this is a daylight. And if you see, it is slightly skewed towards the violet side, okay, rather than red or this thing. So this is sodium. Okay, you see sodium light. I don't know these days whether they have these sodium lights or mercury lamps, but earlier when we were small, street lamps used to be either sodium or mercury. So if you remember, anywhere sodium lamp is sodium vapor lamps. So sodium produces a characteristic radiation, okay, around 5,900 Armstrong, and it is yellowish. So because depending where it is, that color light is emitted. So characteristic radiation. Whereas the mercury, in the mercury vapor lamps, you would see it is more towards the blue and violet side. So the light of the mercury vapor lamp was bluish, not blue completely, but bluish. And as a result, so both these lights now, of course, we use LED lights and different kinds of lights, but they were sturdy and they lasted for many years. You don't have to go and change the street lamp every time. Okay. So which is continuous spectrum, the light that we get from sun is a continuous spectrum. All of them are present in a continuous fashion, but the intensity may vary here, as you see. And the wavelength here depends upon the temperature of the material. When you heat something and not the material, irrespective of material, when you heat more, you will have more of that light which is coming. Whereas line spectra could be just single, mono, or it could be multiple, and they of particular color. And this has nothing to do with the temperature, but only the material, because each substance would have specific, and that is what we have learned in the atomic structure. Briefly about radioactivity. So we already talked about Marie Curie. So if you look at so the radioactivity she first described, of course Becquerel was there, but she isolated radium, where we should not forget Becquerel. Okay. So if you look at this is number of protons and number of neutrons. So this solid line is if they were equal. As you see, the number of protons are increasing, there are more of neutrons. For some time they are fine. After that, the nucleus becomes unstable. And it becomes unstable, then it decays. And not only heavy rare earths decay, undergo radioactive decay. Decay means it is breaking up. That's what we call decay. Okay? And I will just show some of the examples of this radioactive decay. And basically, all this blue part is when it is decaying by giving an electron or negative beta particle. And this yellowish thing is when it is giving a beta plus, which is a positron, positively charged beta particle. And then, of course, alpha, you see this color alpha emission happens only in very heavy, radionuclide. Okay? Like uranium or plutonium, which are very heavy, which has so much of things they have to lose that in one blow. They just helium alpha particle is basically two proton and two. So this is the alpha decay. So in an alpha decay, you have seen that just plutonium is so heavy, it every atom wants to come to a stable state. It is a desire to come to a stable state. So it decays with emission of two protons and two neutrons, and which is what we know is called as alpha particle. And if you see that here it is Q. So how does the energy come? You said, okay, so we have released that it should be equal, but there will be difference in the mass of what plutonium and the uranium-236 plus the alpha particle. So this difference in mass, that's where E is equal to mc squared. That mass into c squared is the energy that will be released, and that will be in the form of gamma rays. Okay? So that is what how it is. You will see everywhere this Q. So the value of the Q, which is the difference in the masses converted into energy. Now beta decay. Beta, here we're talking of electron. Okay. For normally a positron is called, the positron is basically a positively charged particle. So in this what happens? Neutron is converted into a proton, because neutron, if you take a negatively charged particle, remaining is positively charged. And so neutron becomes a proton plus electron, and an anti-neutrino. So neutron remains inside, and of course here also there is difference in the total masses of the two substances, and that is released as energy, which is gamma. Okay, so beta decay. So beta plus decay, this is the beta plus decay, which is on this side of this line, this yellow. Beta negative or electron decay was this bluish upper part, when you have more, even more neutrons. Okay, when there's more neutrons, and this is this yellowish part in there, which is a yellow or khaki color, which is a positron decay. It converts a proton into a neutron, a positron, which is an anti-electron, and a neutrino. Okay, that is what it is. And this is more common in radionuclides or atoms which have a low neutron to proton. Okay, so this is low neutron to proton ratio. That's when you will see this. So this is just shows some of the characteristics. So the ionization. Okay, so alpha particle ionization energy is 5.5 MeV. Mean ionization. So when you will later on read the radiobiology and the heavily ionizing and sparsely ionizing, it is very high, mean density. Okay, this density means ion density in ions per micron of water, but the range is very less. It is so heavy, bulky, charged particle. It just even a paper is enough to stop it. But wherever it is stopped, it gives releases a lot of energy. Then beta particle, it is the energy is less. Ionization is not as intense, or the density of the ionization is not as much, and because of that it can travel far. And this all has a bearing on how we use these particles, because although we use photons, ultimately it produces electrons, and that is what it causes. So you have to remember this beta particle is very important. And beta particle could be low energy or high energy also. Even high energy, the mean ionizing density is little more, but still the range is quite substantial. Okay, and photons, we know it is indirect, and that produces electrons, and that is mean ionization density. Positron I'm not talking about, because positron emission tomography, that is only for the diagnostic, that is in terms of treatment, it is not applicable. And when we talk about imaging, we will discuss about in more detail about positron. Okay, so I had shown this picture, and now I will talk about briefly for production of X-rays, and then we will, this first lecture would be over. So this is Röntgen. So of course his X-ray tube was very primitive. That wasn't very good. I could not get a good picture which I could show. But this is a basic thing. What is important as anode and a cathode? There's a heated filament, thermionic emission. So thermal energy, you give thermal energy. Any metal has a property. There are always some free electrons in any metal. Okay, metals are good conductors also. They are free electrons, and when you give a high enough dose, some of these electrons will just escape from the surface. So, and once they escape from the surface, the fate could depend on what happens, what the surrounding, and what happens next. So, if when they escape, so thermionic emission of heated filament, and the filament also ideally, so I'm not getting into details of the type of filament. They should be high Z material, like a tungsten or other kind of filament. And when it comes out, then what happens? The filament should be able to withstand heat, because if heat if melts, then the filament is itself not there, or the current will not pass through it, and it will not get heated. And then if there is electrons are negatively charged, if there is a potential difference and there is a target, they will run towards it. But remember, air is also matter. All air is there. There was a vacuum here completely. Without that air, all of us will die within few minutes. Okay, so air is also a matter which we don't see, we don't feel it in a still place. So air is evacuated, so the electrons go, run, and hit the target. So anode, cathode, from there it comes, hits the anode, and then there is a window from which these beams come, and there is a collimator system. This is a basic. So within 10 to 20 years of Röntgen showing that there could be X-rays can come, you can take X-ray. All these basic technology was developed. There was a Coolidge, tube and other tubes, and later on the X-rays, what we use it for medical purposes, were developed soon. So this is a picture I have taken from somewhere, but in our museum, in our department of radiation oncology, we have the same X-ray tube. Actually, this one also where we showed, this is a fixed anode. This also we have, which is broken in two pieces in the glass pieces. If you all see, you will also notice as a window. One day, I think as a part of practicals, you all should see that. Once you see it, you understand it much better. I should have got it here today. I forgot about it. Okay. So in our museum, we have a fixed anode X-ray tube also, which is broken into two pieces. And we also have this rotating anode X-ray tube. So again, so there's a glass envelope. Within the glass envelope, there is vacuum. Vacuum is created. So from here, these cables are going, the electric current would be passed. And there's a cathode. This is focusing cup, from where the electrons, thermionic emission of electrons will be focused. This is a rotating anode or target, and this is a rotor which sort of rotates this. Okay, so these are the basic components. So this looks very simple, but with a lot of innovation, this was developed and it works very well. For the desired range of X-rays that you want, this is a perfect machine. You can't make it better if that is the desired range of X-rays that you want. So this is looking at sort of a frontal view of the target. So this is looking at it from the side. So anode disk, what we call, which is rotating. Okay. So the electrons come and hit on this part, which is this part, which is there. So there are two questions. So when I said we are having this course, there will be an exam also. Okay, after a few weeks, it will be online on a Google form. Just quickly, it will be just quick this thing. So the questions would be, why to have a small focal spot? Okay, what is the advantage of having a small focal spot? That is important. Where is the focal spot? Why it is sort of this? Why it is an inclined plane? Why it is not straight? Okay. So this is why it is not straight. Why it is inclined? Why to have a small focal spot? And why rotate the energy? Okay. So if you know it intuitively or you have read about it, that's fine. But if you haven't, if you do not know, please read it and understand for yourself. I will not tell the answers. If I tell you, will say, "Oh, it is obvious." And once you think that was obvious, these are things which you forget most easily. When someone tells us, "Oh, that was very obvious." Okay? So you please read it for yourself, and then in the exams, we will ask. Now, I have taken these pictures from Meredith Massey. I really love it because of simple explanation. These things will not change. After 1,000 years also, it will not change. Okay. So what could happen when a highly energetic, fast-moving electrons enters a high-Z metal like tungsten? So the target is made up of tungsten. Okay. Remember, we're talking of different metals, so it's made up of tungsten. So it just goes there. Okay. And when you say high speed, there are various ways of defining the speed. Speed is also increases the energy. So just look at the fate of number one. Okay, number one goes here, there, everywhere, and then it is deflected. So here H means produces heat. Produces heat, again deflects, produces heat. It produces a photon. Okay, this photon, then it is deflected, and then in the end again it is almost deflects 180 degree, again produces a photon and it is stopped. Okay, so it has produced heat at few places. Number two, deflects, produces heat, again deflects, produces heat, deflects, again produces heat, and then again deflects and goes out. Imagine like a football player, very good. He just goes, takes the ball, dribbles there, and from this end to reaches the other end, and then out. He is out. Nothing he has done, just lost his energy. Okay. And so what happens? This electron has lost its energy, but in the process has heated the metal, the tungsten. This number one has lost all its energy. In the end, it's done the goal and lost all its energy, and in the process it produces twice. It has produced a photon. This one energy in the first shot itself. Okay, it has lost all its energy, and entire energy of this electron is converted into a photon or an X-ray. Number four, it does again two things. So you look at it, it is deflecting from in different angles of deflection. It is slight deflection, then major deflection, then it is 180 degree deflection, etc. And this, and when there's what is shown outside, this is the electron cloud, and inside it is a nucleus, I should have said. So this is what it is happening. And in the process, what is happening? It is producing X-rays and also producing heat. Heat is something which we don't want. X-rays are something we want. And X-rays, ideally, we want pure one energy X-ray, 300 kV X-ray, or 1000 kV X-ray, or 2000 kV X-ray. But what is happening is that X-rays are being produced by different degrees of deflection and different kinds of hits. So you will see a spectrum of X-ray energies will be produced. Okay. So you have to keep this in mind, because later on you will have to deal with this. Okay, whatever is happening in the target, you have to deal with it. Otherwise, it is just this thing. So it is producing a spectrum, continuous spectrum of energies it will produce, and also heat. So look at the amount of heat production for a 60 kV. When you say operating voltage, okay, when you say 60 kV, that means the operating voltage, that the voltage difference between the anode and cathode is 60 kilovolt. Okay, how much is the electricity that your supplies is much less. Okay, 220 or 240, and in United States it is half of that. Okay, so this is in kilos. It is much higher, but 60 kV, 99% is heat. It is just going running here and there without any purpose, and just only little bit is produced in as X-ray. Even at 200 kV X-ray operating voltage, 99% has gone into heat. But as of course, even at 20 MV or 4 MV, it's not that it is not producing heat, but the heat produced is not So in the kilovoltage era, all radiation oncology physicists, the X-ray machine will go bad and get heated up. And as mentioned, not only heated up, the tungsten filament also is to just, all these things. So the vapors used to come out, vaporize, and they will come and line the coat. If you see a very old X-ray, they will be coating or lining of this tungsten. And because tungsten is a heavy material, it will filter out your radiation beam. If you want just 60 kV X-ray, that tungsten film will, reduce that. So this is a very important. Now, so the beam which is coming out of an X-ray tube, we are showing this beam which is. So there are four things that you would see in this diagram, and I'm not going to tell you. This is what you'll have to think and get it right for yourself. Again, this will be as part of your, understanding how much you've understood. So you look at line A. That line A, that means maximum intensity is here. So peak intensity. So this is for a 200 kV. Okay, 200 kV operating voltage of this machine, X-ray machine. So one is line A, then there line B, then C here. That is where X-ray starts. It is not starting at zero. Here the zero looks like it is very close to it, but actually zero should be at this intersection of this. So it is starting maybe 5 or 10 kV. And then there is D and there is E. So what causes these things? A, B, C, D, E. And are they of any clinical relevance? Ultimately, I mean, we are not pure physicists. We are not doing it. Ultimately, we are learning physics because if it has any clinical relevance, either in diagnostic radiology or in therapy. Okay. So what causes it? What is its clinical relevance? And once you know what causes it, finally, can you tackle them? If they have clinical relevance or adverse effect, can you tackle it? So this A, B, C, D, E, please all of you read. I'm not going to tell you what it is. It is again because why I'm not telling you. If I tell you, you say, oh, that is obvious. And whenever you think something is obvious, that is something you forget most easily. Okay. So some things you have to. The best way to remember is or learn something for long is you think about it and you get it right. And if you've got it right, not just by a stroke of this thing, this is correct answer. That is something which you will very rarely ever forget. So even before reading, these days very easy to Google everything. So even before reading, you think about it and see if you can get it right. If you get it right, you don't have to even ever read about it. So this is X-ray spectrum from tungsten target at different operating voltage. Okay, this is 50 kV, 100 kV, a little less than 60 kV, 90 kV, 120 kV. Okay, so again you see A, B, C, D, E. What I had described in this A, B, C, D. So when you look at this one, you will get an idea as to maybe if you are clever enough, you will figure it out what is happening. Okay, but it is important for you to know this. One thing you remember when we talked about, I will show it here. So the photon energy, so filtration. So ideally, you do not want very low energy, beam, and you want to have only high energy beam. Okay. So this is a desirable, but why the desirable is not practical? Okay. Again, you have to see. So you can say, okay, I want to tell your physicist, I don't want this low energy from this. I have got a 400 kV X-ray machine. Why are you giving me so much of 100 kV X-ray? I don't want this. So remove karo. Okay. He or she will say, how can it be removed? You say, do something. Okay. My guide teacher used to tell me, I do something. That means you figure out what is to be done, but I don't want this. So this something which is desirable is not possible. So why, or it may be possible but not practical. So again, for you all to remember, see, ultimately, always you have to be reasonable. If you are not reasonable, and then you just keep on asking something which is not practical, in real life, it will not work. We are talking of clinical medicine, either diagnostic radiology or radiation. So this is so filter. Of course, nowadays we don't use filters, but in exams, quite possible there will be a filter kept. Thorius filter. Thorius was a Swedish physicist. Okay, Many new departments will not have, okay, but any old hospital, old hospital would have a Fourier's filter, and in that, so the compound filter, okay, so unfiltered, this is tin alone or tin with copper and aluminum, okay. So what is the principle of a compound filter? That is important, and this is something again I will not tell. You will have to read. Okay, just important that it is important compound filter, because in the exam it will be asked. Then direction, most important. Okay, you figure it out. You just read it and you figure it out. This helps in this. So which will be the direction which will be facing, whether tin will be facing the X-ray from the X-rays produced or the aluminium. Then you say, okay. So unless until you know the principle of it, you will not be able to answer that. So I mean, it's only one direction. It could be either facing towards, either tin could be facing towards the X-ray, or aluminum could be facing. So when people have to make, it's like a toss of a coin, 50-50. Most people hesitate when they are making a guess. 50% chance they'll be right if it is just a blind guess. But we can make out this person is hesitating. So then you ask the question in the other way, then they will say, I'm not sure. Okay. And when you say I'm not sure, that means you have not understood the principle of using. And that is most important. Once you understand the principle, if someone asks you this question, you will say, what a stupid question. Why are you asking this? Obviously, this is how it has to be used, because that is the purpose of using. So then is a concept of half value layer. You will see, okay, half value layer. Now we deal with only in terms of radiation protection. Okay, how many HVL are used, or sometimes in deciding the shield when we use how many HVLs of shield. But in the X-ray period, HVL was used mainly to define. Also, one of the main purpose of using HVL was to define the quality of radiation. Okay, because higher end quality means higher energy, more the energy, it will be more penetrating, so the HVL value would be more. So this is, if you look at, is the HVL of broad beam versus narrow beam. So in the narrow beam the HVL is less, and in the broad beam the HVL is more. Okay, so that means it is, and why it is, because of the scatter which reaches, ultimately you are measuring somewhere. Okay, so that is what is in a narrow beam and broad beam. So most of the measurements are done in the narrow beam. Okay, so when you say, you have to define, you open the field so much of scatter will come, it will look as if the HVL is more. So this is the last part of this question. So the superiority of hardening by the tin copper aluminum filter for 200 kV radiation. Each of the four filters pass the same amount of radiation. Okay, so this is the HVL for tin copper aluminum compound. The HVL is 2.0. That means the most energetic beam, highest energetic beam with this filtration, without impacting the intensity much to a greater extent. So this you have to figure it out for yourself, why this is the best way to harden the beam, what we call hardening of the beam. Hardening of the beam, or improving the quality of the beam, or basically increasing the energy of the beam, the mean energy of the beam. Okay, which is best. And as you see, at a higher energy, like for 1000 kV or 1 MeV, by adding lead, you have very little impact. Of course, there is some hardening of the beam, but not as much. Okay. So to finish this, the mighty X-ray tube taught us the power of ionizing radiation. It is not used. It is in museum in our department now. How to give X-rays and how to give ionizing radiation. And they ruled the first half of 20th century, and they saved millions of lives, and they have not become completely obsolete. In most of the countries like India, in radiation oncology department, we don't have an X-ray machine. But if you are working in a country where a lot of Caucasians live, where skin cancers are common, then these X-ray machines have special use for treating skin cancer. In many ways, they are better than electrons. You can have the geometry, you can customize the size, small size, and they could be treated very well. Okay, so they're still not completely, and of course in diagnostic radiology, It is there for sure. So now we will cover the interaction of X-rays. After that, we will have a break. Okay. I also need to give my voice some break. So on the same thing that we were talking about, we'll talk about the interaction of X-ray with matter. So we have chapter 1, section 1 to 3 of AAPM-ASTRO we have covered. I not want to detail. Now this is section 5. 4 will come later after this. So because in continuity I will be talking about this. So interaction of X-ray with matter. So this is required how, both to understand how X-rays are produced and can be used inside human body. We need to know how different types of radiation interact with different types of. So if you remember, I was talking about a canvas and the painter and the coloring tool. All this is important. Okay. So when traveling through any media, how much of the incident means the radiation beam which is coming on that surface of that, on the metal or the body or a phantom, whatever it is, how much of the incident is absorbed or scattered or weakened. Weakened means attenuated is the scientific term, or exit out. It depends upon few things. One is the radiation type and energy. Again, I know it is very obvious, but need to understand why different types and energy. And the matter, the type of matter and the amount of matter it passes before entering the body and inside the body. Why I've added before? Because before it enters also there is air. Before air there is the material which is there. It could be a wedge filter. It could be a flattening filter. It could be so many things. So your beam is not just produced and just comes from there. So it has passed through many things. It may be passing through the shielding tray. It may be passing through the blocks and all those things. So everything is affecting the radiation beam. Because whenever radiation interacts with any matter, it will have some interaction and it will have some impact on the beam. So what is it? We are interested in a clinically useful radiotherapy beam. Now we're talking of mostly radiation therapy, not for diagnostic radiology. I have not talked about that. So a clinically useful beam we should be able to shape it the way we want, because tumors are not round or square. Can be given from a direction we want and focus to areas we want. When we are doing the planning, because we are the artists, we need to know how we need to draw, and can be modulated in terms of the intensity that we want. Okay? Because we have to decide, okay, I want to this much, and when the beams are intersecting, what is happening. So then only it is a clinically useful radiotherapy. Otherwise, it is not clinically useful. So on the right side, you see this is a cloud chamber. Okay, I think it is Rutherford. I've taken it from Meredith Messi. This is a straight line, sparsely ionizing electron, highly energetic electron. Okay, and then this is when the photon is going, it sets in motion a low energy electron. A low energy electron is more densely ionizing, and in the end, electron is also a charged particle. Sometimes we forget that electron is also a charged particle. Only proton is not a charged particle. Electron is also a charged particle. It loses all the energy and it just stops there. Okay. And this is usually a picture, X-ray picture of lower limb. It shows femur with a fracture. It shows a metal nail inside and a ring from outside. And then you can see some soft tissue. So this picture is produced because, and this is X-rays, the diagnostic X-rays, it could be 60 kV X-ray or 90 kV X-ray, whatever, something like that. Okay. So there the interaction is happening with different kind of tissues. X-ray doesn't know tissues, it only knows atoms and molecules. So the different kinds of atoms and molecules includes hydrogenous material like soft tissue, living tissue like bone, which has more of calcium, and then a metal, and different things have produced a different kind of. I will only say, we take X-ray, it is the exit door. So whichever looks more white, that means there more of the radiation has been absorbed or attenuated. There are two ways of weakening of the beam, because less has reached the X-ray plate. Less of it may have reached the X-ray plate either because it has been deflected from its path, scattered, or because it has been absorbed. Both would cause weakening of the beam. And this effect, differential effect, gives the contrast. Okay, so this we will show later. So what could happen to a photon in its attempted passage through the matter? You know why? Like because the language it uses, okay, it attempts to pass through matter. So one is it may be deflected from its original path and henceforth proceed in a new direction, but with unchanged energy. So nothing has really happened to it. It is just changing energy. Okay, could be deflected, but also in the process lose its energy. So it is scattered and attenuated. First is only scattering. Second is scattering with attenuation or disappeared altogether. Okay, absorb. Okay, when it is absorbed, always attenuated, absorbed, or transmitted unchanged, nothing happens. So it is neither scattered nor attenuated. Okay, there is always a probability of each of these. So you remember these are the four possible things which could happen. So the first and foremost, the most important is the Compton's scattering. Okay, Compton effect of Compton's scattering that I will first explain. So in this, the incident photon it interacts with the free electron. Okay, the free electrons for it, the electron cloud. If you remember how the Compton effect depends upon the electron density. But the only thing it depends upon the electron density. So it interacts with the free electron. And it is scattered in that direction. They have given this angle phi. Okay, it is scattered through this. And the recoil electron, the electron which it has interacted, moves with a different direction, theta. So in this process, it is transferring some of its energy to the electron. And the energy that it transfers depends how much angle of this theta is there. If it is 180 degrees, then it transfers all its energy, maximum energy. And this will also cause a change in wavelength because it has lost some of its energy, so its wavelength would change. Okay, so this is a Compton scattering. Compton scattering, it will happen. So it will produce Compton scattering is producing both attenuation and scattering. So the recoil electron, what we are talking about, this recoil electron, if you see it at different energy levels. So the primary photon could be, they have shown from 12.4 keV to this is 1.24 MeV, 12,400 keV. So obviously the wavelength is energy is according to wavelength they have chosen. And the scattered photon, if you see in the lowest energy, almost scattered photon has got almost all the energy. Okay, and the scattered electron has got much less energy. And when there is a higher energy, the scattered electron has got so much of energy. Okay, so this really the photon has less energy and electron has more energy. So this is what the photons they call indirect effect to the electrons that they produce, and we're talking of mega voltage. So as the energy of the primary photon increases, the energy transfer to recoil electron increases, and the scatter decreases. So this is also another factor you will see. More high energy, X-rays or beams have less of scatter. Okay, so it is less likely to be scattered, and the intensity of scattered radiation is also less. So these are the important factors that you will see later. So putting all these together, ultimately you have to just sum it up. So sometimes when you look at the diagrams and all, you have to remember there were three things. There was absorption and there was scattering. And scattering without, so it could be either causing attenuation. Attenuation means the reduction in the intensity of the beam. So total scatter attenuation is equal to absorption plus scatter. Okay, either it has been absorbed or it has just moved away somewhere else. It will be there. Okay, so and then scatter decreases as the photon energy increases, that we have seen in the previous thing as we increase, and the total attenuation is less at higher energy, that also we have seen. and the absorption by recoil electron increases steadily as the photon energy increases up to 1 to 2 MeV. After that, the pair production dominates. The other is the direction of scatter. So low energy scatter, it is generally isotropic. Okay, so it scatter in all directions. If you look at it, a 10 kV, whereas as you increase the energy, it is more of forward scatter. Okay, more of the forward scatter, and the total scatter also reduces with increasing energy of radiation, and the spatial distribution, because there is not happening isotropic, it is more of forward and the narrower. So when we talk about the radiation beam which comes out looking, and why there is a need for a flattening filter in the modern LINAC, that is based on this principle. So the photoelectric effect is very important. Again, we asked this many times, people just get confused. Very important to remember is it is first of all cube. That means it's a cube when it's a square. Talk of inverse square law, you know how much difference it makes. Here it is the cube. And for the Z, it is directly proportional to the cube of the atomic number. That means the moment you make the high Z material, photoelectric effect will just go through the roof. Okay, that will become the most dominant. And inversely proportional to the cube of the primary photon energy. Okay, so it will be most maximum when a low energy X-ray is interacting with a high Z material. Okay, so both are working. So one is directly proportional to the cube of the Z and inversely proportional to the cube of the energy, which is denoted here as the HV. Okay, so that is very important. So in clinical radiotherapy in the deep X-ray era, that is where it caused toxicity. We will talk about it. And pair production, we will not discuss much on this. Just to say that in this the photon disappears, gives rise to a electron and positron. Energy is equivalent to the mass of this pair. You know, by the formula is equal to mc square, and 1.02 is the threshold required for pair production. Okay, I don't think I've written, so you all should think why 1.02 is the threshold. Okay, you should know the answer. I mean, this is something which you might read and you'll get it, but if you haven't, you go and read and find out why there is a threshold energy for pair production. Okay, it produces two photons of by annihilation reaction of 0.51 MeV each, and it is directly proportional to Z and the incident photon energy. So it is, whereas earlier it was to the cube. Okay, and so if you put everything together, okay, this is a summary of attenuation, because finally, whichever way is happening, we have to see how much of the beam is attenuated. So scattering decreases as energy or kV, when both ways express increases, and is mainly independent of Z. Photoelectric effect is cube of directly proportional to the cube of the Z or atomic number, and inversely proportional to the cube of the energy. Pair production is directly proportional to the Z and energy, and this is beyond 1.02. And when you add it all together, this is what you get in the total attenuation. So this is again, which is shown. So there are two. One is water, other is copper. Copper is high Z material. Water, the Z is 7.4. In this copper, because it is a high Z material, photoelectric effects predominate for a longer time, whereas in water, photoelectric effects for less time, and Compton effect in water is spread over a wider range of photon energy. Important to see that pair production, both the places, irrespective of the Z or the energy, its starting point is 1.0. Before that, there is no pair production. Okay? I think that's a more important point, and I think that's what it is written. And I think the same thing, because bone and muscle, soft tissue, and the one which has high calcium and soft tissue around that. So now we're talking about, one is the scattering. Okay. Now attenuation, exponential attenuation. So exponential attenuation is by a given thickness of a material, a constant fraction is being attenuated by using a linear attenuation coefficient. So thinking it is little difficult. So this is a fraction per unit thickness of material. And this is when we are considering uh, thin layers, since each layer reduces the radiation reaching the subsequent layer. So when you're talking of thin layers, okay. So so you got material A, material B. You have different, in different thicknesses. You have different relative intensity, and so the it will depend upon high Z material, which will attenuate more. It will increase with increasing thickness, and higher energy beam is less attenuated by a given thickness of the, like, let us say the 5 centimeter thickness. High energy beam has less attenuation as compared to this thing. Similarly, for the same thickness, material B versus material A has a high Z, so it will attenuate more. Okay, so all this is, so it is not just so the clinical relevance of this, when deep X-rays were used for treatment, the bone absorbs much higher energy. So ultimately, we were interested for a diagnostic radiology, because it absorbs more, it will give a contrast. But they're giving so little dose. They are very happy. You get a good contrast. You can see differentiation between bone and the air and the soft tissue. But here we give radiation. We are not interested in taking the exit dose of radiation. So when we give radiation, if one part of the body gets higher than what we want to give, it can be a problem. So in when photoelectric effect dominates, and bone has a Z of 13.8, water has Z of 7. Okay, water has Z of average, because water is also composed. So then it's much more. Okay, muscle, water, 7.4. Yeah, it is. So at lower energy, because the predominance of photoelectric effect, it is absorbing much higher dose, and that could cause problems. Okay, this is another way of looking at it. When, because the scattered electrons have a finite range after some point. So this is a soft tissue absorbed dose, and the bone absorbed dose could be much higher. But as you go in the center of the cavity, because the scattered electrons would not reach their range in the bone, will not be so much. So in the center of the cavity, the dose is again come back to the normal level. So the marrow is not completely fried. Okay. This is again depicting it in a different way, in a small cavity versus large cavity with bone. What is the soft tissue absorbed dose, and what is the bone dose? So this would be one exercise all those who have not yet done the MD should try to do. Read out, even if you read from somewhere, if you fill this table, it will help you to, when you're reading it and writing it, then you will get to know. So RADs to Rontgen. Okay. So what is Rontgen? Rontgen was a previous this thing of exposure. RAD was absorbed dose. Okay. So of course now we don't use RAD this thing, but again for you to understand what will be happening if you put a 100 kV X-ray to 4 MB or a cobalt 60. So what will be the RAD to and both in soft tissue as well as in bone. So while you're doing this exercise, it will become clear in your head as to what is happening. Again, this will be in the exams that we will told. Okay, so now we come away from the basics to more recent things that you would associate with, which is production of mega voltage radiation beams, properties of a clinically meaningful, clinically useful beam, and the beam modifying devices. So which in the Astro APM, it is section 4 and 8.1, and the other parts, more advanced parts, will be covered in subsequent weekend courses. So it's the art and science of modern radiation. So we know Linacs and telecobots, they produce high energy mega voltage radiation. All this while we have been discussing what are the issues with the X-rays or the kilo voltage, but we also said there's still treated and cured so many people, but now they had problems. Beams are shaped and directed on tumor, and the intensity is modulated. Spatial distribution of absorbed radiation is based on its type, energy, and interaction with matter before and after in body. So I'm again saying that, reiterating that you have to get it into your head that that's so many things are happening. And for a given absorbed dose, the exposure dose of each beam is calculated, delivered, and monitored. Finally, that is what it happens, because you might have a fanciful plan or you may have a desire, but how from that particular beam, what should be the exposure that will come out of the machine on the patient, that you have to calculate and monitor. So, showing this X-ray tube, how do I? Okay, let's take this thing. One second. So if you look at the earlier kilo voltage, 100 to 250 kV X-rays, the bone was getting much higher dose, and the skin and surface dose was also high. We had not talked so much about the skin and surface dose, but in clinical radiotherapy, that is also important. And on top of it, all the things that, of course, you have to answer, even by the best filter, you can increase the energy only that much. Beyond that, you cannot change much. So that was a time that we need something else. Okay, and this also we have discussed the reasons for this, the photoelectric effect, and the scattering in this in the low energy X-rays. So a replacement for kilo voltage X-rays for therapy had to be found because of the lower percentage depth dose. So it was difficult to treat deep-seated tumor. That is the first and foremost, because if you can't give enough dose to the tumor, you can't cure it, and sometimes can't even palliate. So, I mean, you're out of business. But even if you are able to do that, the skin used to get the higher dose. There was no skin sparing effect. The other name of mega voltage radiation is also skin sparing radiation. Okay? So, skin used to get a high dose, and this was often the dose limiting. In the very early days, this was one of the form of dosimetry also, the erythema dose or other things. So skin would get full dose, and generally skin will break down. You would have moist desquamation, and you will not be able to give further radiotherapy. And that decided that although you had to give a curative dose, you cannot give, because you can't treat through a skin which has already had moist desquamation. It will become worse and might have necrosis. Then, as you have seen, the scatter is so much. That's why you can't shield, even though you may have a shield and you may want to shield a lens or something else. The shielding after a few centimeter depth, it will be all so much of scatter, the shielding would be ineffective. And lastly, which is because higher dose to bone, and the risk of radial necrosis because of photoelectric effect dominating at the low energy. So far, we've been only talking of bone and photoelectric effect, but the other things are also equally important. Now, because we talk of clinical radiotherapy, after we had cured some patients, and we realized that only some patients can be cured. A vast majority of patients who require radiotherapy, they have eminently radiocurable cancer with a deep X-ray machine, 250 kV, 400 kV X-rays, you cannot cure, because either the skill will not tolerate, or the beam that will come in there will not be adequate, and it will, a lot of scatter, and normal tissues will get unintended radiation. So, that time is people of my generation, actually before me, there was a fat yellow book, not very fat. Every radiation oncologist had read that book, Gilbert Fletcher. Gilbert Fletcher, he is, sorry, can I remove this bar somewhere? How to get rid of this bar? I was not getting this bar earlier. Okay, I think that's all right. Hide floating meeting controls. Yes, got it. So, Gilbert Fletcher, he perfected the art and science of reading. In his book, people used to vouch, it is written in Fletcher. If it is written in Fletcher, it was gospel truth. You have to follow that. And why it is written, or why something else is not written, you would just not push. Okay? Fletcher has said that. And see, those days there were many oncologists, radiation oncologists. They would dabble both with technology and biology because they wanted good for their patients. Okay. So he has a lot of work on what is the dose required for subclinical disease. Okay. A node which is not, subclinical, what is the dose required for macroscopic disease, what is required, depending upon how big the lymph node or the tumor is, how much more dose is required. So that concept. Plus, in the gynecological brachy applicator, Fletcher suit applicator, so a lot of those things because that was this thing. And for telecobalt development and its clinical applications, he had seminal contribution. Okay? So you may not read his textbook, but all of you should at least remember his name. There are thousands of people who have contributed. We stand on the shoulders of giants, but at least few names we all should remember. And Gilbert Fletcher is one of them. Okay. He worked, I did not mention that, he worked at MD Anderson Cancer Center in Texas. Okay. MD Anderson Cancer Center is already very famous, but I'm sure people like him contributed to their fame. So this is a cobalt 60 teletherapy. This is a basic thing. Before it became, and I'm showing this as a head, even before it became a isocentric machine, there were different kind of machines. In Tata Hospital, very early on, we had a Janus machine, two-headed. So while you are setting up a patient in one room, you are treating the source goes in the other room and you're treating the patient in the other room. So it is just to economize time. You are setting up here, like in Proton. Now we have three gantries. While we are setting up patient on one, in Tata Hospital, we have an Actrix, we have a Proton machine. The second and third gantry will be clinically commissioned soon. So in Cobalt also, there was a machine like in our old Cobalt basement, we had this Janus machine. So essentially, there's a radioactive source, cobalt 60 source, and there's a source drawer. And when it will come here, the opening, so there will be field light here. These jaws and collimators, they will open and close, and you will get this thing, and you have tray for the accessories. And while you're doing this, so there are collimators, primary collimators, and it is all housed in a lot of high Z material, okay, including sometimes depleted uranium because it is high Z. Depleted means not radioactive. I would accept maybe some trace. So this was for radiation protection, and because this increased the weight of the machine, so you have to get good mechanical stability. And later on, they worked out around that and made it an isocentric machine. Okay, many of you would have seen. Actually, in some departments, they would have never seen a cobalt 60 machine, telecobalt machine. Okay, so for them, it is only through pictures. So any one of you, whenever you go to a city where there's a hospital which has a telecobalt machine, you should go and see. A lot of mega voltage radiotherapy, modern radiotherapy is based on what we learned from, telecobalt. Atomic Energy of Canada Limited, ACL, they were the main source of telecobalt machines all over the world, the Theratron series. Then in France, they had some machines and some other places. So they were the workhorse. Okay. Of course, the amount of energy, so it was 1.25, that is written the half. Average energy is 1.25 because 2 gamma rays, this thing, and the half-life was also once every 5-6 years, you would change the source. So this was a good machine, and you could do a lot of radiotherapy mega voltage without having the problems of the kilo voltage. Okay. And in kV, even if you say 1 MV, if it is produced as an X-ray, when you say 1 MV, the average energy is not 1 MV. Okay, it is much less than that. And now you have to read, because I have said what is all those A, B, C, D, you have to find out how much is the average energy of X-ray machine. If the kVp, maximum peak kilovoltage is this much, how much is the average energy? It is less. Okay. And at the same time, around the same time, another radiation oncologist, Henry Kaplan, okay, So he did a lot of work, and he's not he alone, along with his physicist, one of the first linear accelerator to be used, make it clinically useful. Just having a linear physicists had linear accelerator earlier. Okay? In 1950s, 1960s, so much of physics research has happened. But to make it clinically useful, I think that's the trick. You have to use it for directing a beam on a patient on a tumor to cure. That is completely different this thing. So he was involved in this, and the first patient who was treated was a 2-year-old boy with bilateral retinoblastoma. He had already lost his one eye, and the other eye had to be treated. While so we didn't, no one wanted him to become blind because of the after effects of radiation. So this is when this linear accelerator was used for that. And of course, in the first prototype machine, by now so many changes have happened, but the basic design of a linear accelerator has remained the same. And I will also talk about him, Henry Kaplan, not just LINAC. Hodgkin's disease, all you know that's mostly chemotherapy, some radiotherapy, but a systematic evaluation of Hodgkin's disease. He is the man, Henry Kaplan, who did at Stanford the systematic evaluation of Hodgkin's disease, the staging laparotomy, when you should use radiotherapy, when you should add systemic therapy. So a seminal contribution of Henry Kaplan. So again, like Gilbert Fletcher, he was not just looking at technology, also the biology and tumor biology and this thing. Same way Henry Kaplan. On one end, he was in technology. On the other hand, about a disease, understanding the disease inside out, and a systematic evaluation in the treatment approach towards the disease. So this is a basic linear accelerator sort of schematic diagram. Of course, you have to have a stand in the RF power generator, radio frequency wave. The electron guns will come, which will inject electrons on the RF wave. There's a waveguide, which is the accelerator, in which they will serve the electrons will surf on these waves and become more energetic. They will gain more speed, and when they gain more speed, then they are, because electrons are negatively charged particles, then they are bending magnets, then they are sort of bent, different degrees, depend which degree you want to bend, and then they hit a target. The earlier target that I had shown you for an X-ray machine was not a transmission type; it was reflection. They used to hit, and the beam used to come out. This is transmission. Here the beam sort of hits there, and then the X-rays come out from the other side. It is not that X-rays are coming deflected somewhere else. And then not just that, because ultimately it has to be a clinically useful beam. So you have to have the whole thing. So you have to have the patient's couch, then this gantry, or this will move, because remember we have said we want to give radiation from different directions. And then the collimator, which again could move because we may have to change the shape. There has to be an accessory tray, shielding tray, where you can put shielding devices or whatever else is there. And so this is how the modern linear accelerator works. So this is how it shows the production. So electron beam is coming, X-ray target is there, and through this X-rays are produced. The primary collimator, they're not allowing it to sort of this thing. And remember, geometry, this travel in straight lines. So you just simple geometry, you will know how the beam is sort of where it will come. And when in the X-ray mode or the photon mode, this carousel carries the flattening filter. And this you remember when we talked about with high energy, it is forward scattering and very narrow this thing. So it is coned down, and this is how the beam it is. And you otherwise get a very small width of the useful beam if you just only use the absolutely narrowed down view. So the flattening filter, we'll talk about it later. And there's a scattering foil, this has come out. And when you are going to use electrons for treatment directly, earlier we did not have electrons. So this thing comes out, the carousel, the flattening filter comes out, and you have a scattering foil. So instead of X-rays coming out, the same electrons which they come, and when they pass through a scattering foil, they are scattered, more of electrons are produced, and then they come out. And because electrons are charged particles, okay, remember, they are not photons, so they will not travel in air in straight line. And for them, air is also a matter. That's why in the X-ray tube we have evacuated, made it a vacuum, otherwise they will interact with the air. So they have a tendency to go scatter here and there. That's why you require an electron applicator to keep them in track, and then they're focused on the patient's body. Okay? Whereas in photons, you don't need an applicator for it to come because they will travel in straight lines. They are photons. They are electromagnetic radiation, whereas here it is a charged particle. Okay? Plus, because it is being produced, unlike gamma ray, radioactive decay, we know exactly this much of amount. This is the rate at which it will decay. This amount of radioactivity will come out. You can measure it once in a while, whatever the periodic checkup is required. At that point of time, you don't have to measure. Whereas when you produce X-rays or linear accelerator on this thing, how much X-ray is being produced, so much things may vary. The electric current, the condition, the temperature, and the amount of X-ray which may come out or the intensity of X-ray may vary. So that's why it had to be measured in real time. So the ion chamber was there, both so two ion chambers were there. Now in different as long as we came out. Okay? So this is a basic design of a linear accelerator. I am not sort of getting into the details of it. We will have subsequent lectures where when we talk of advanced technologies, you have to understand more aspects of linear accelerator. Just understanding the simple things would not help, but suffice for this point of time, this is not. Okay. So this is a good website I found is oncologymedicalphysics.com. So I think they provide training for American Board of Radiology certification, both physicists and also for some doctors only. So I think they have given many simple explanations. I've used some of their, so I don't know whom to take permission, so I just copied them and their website is there. So the same thing, it's a modern Linux. So what we were showing schematic diagram, there's a stand, then there is a treatment head, gantry, and KV imaging system and portal imager. KV imaging system on the sides, portal imaging because it will be the exit beam. So it has to be on the opposite side of from where the X-rays or the photons are coming. So inside of it, the basic this thing is you produce these RF waves. They're showing a klystron or a magnetron. In high energies, you require a klystron. When it is more than 12 MB photons, then you require a klystron. And then the electron gun is there and it goes through a waveguide. So waveguide, again, there are different kinds of waveguides. This is a schematic diagram because we will have a linear accelerator design and advances accessories later. So when it travels through that, it increases the speed of the electron and it through the bending magnet, it bends and then it hits the target, X-rays are being produced. Then this is again the flattening filter and these are ionization chambers. It measures the dosimetry and this is the light source which will tell you how the beam is coming and this is how it comes from the treatment. So it's a simplistic way. So your energy, instead of just thermionic emission and letting it go through a potential difference as used to happen in an X-ray tube, you use additional methods to make it even faster because you want higher energy. And that will not just happen by increasing the potential difference. So that's why you use klystron or magnetron and the waveguide. So these are the essential features of that. So electron gun also you could have diode or triode electron guns which produce these electrons because without electrons nothing will happen. The magnetron, there are various kinds of magnetron and I'm not getting into the detail of a magnetron. Okay, so this will produce these microwave frequencies and when you require higher this thing for a high energy linear, then you use klystron, which is a microwave amplifier. And there are different kinds of waveguide, standing waveguide, and other things. So one thing which I have not shown in the simplistic diagram is the isocenter. And it is very important, crucial to understand that modern radiotherapy, even though it is not a precision radiotherapy, every radiotherapy is precision to some extent. Then the term is high precision. For any modern radiotherapy, unless until it is a palliative, just single one, lateral field or one anterior field, this isocentric approach is very important. So this is a point in space around which everything in the machine will rotate. Okay. Whether it is a gantry rotates, clockwise or this thing, it will rotate around this point in space. The couch rotation is also, if you see, the couch axis is also around this. So when you rotate the couch, it will rotate around this thing. And the collimator is not shown, but even when the collimator rotates, it will rotate at this point. So this is the intersection in the space around which all the movements. And how this helps is in the setup, because we have to treat, when we will come later, we'll talk, we have to use multiple fields, and we treat multiple fields using having an isocenter, and having that isocenter accurate at that place where it is supposed to be, it helps. Okay, so I don't have to impress upon you all. On modern radiotherapy without isocenter, it's nothing. Okay, but this is very important. And some of the earlier mega voltage machines, especially in the telecobalt machines, they were not isocentric. Today, everything is isocentric. So in this TG 142, so for them, the QA for medical accelerators, so they are daily, weekly, monthly, and annual checks. I'm just talking about one aspect just to show you the daily checks. Other details will be covered later as we go on this thing. And what is important is that the tolerance, nothing is absolutely, because things are moving. These are heavy machines. Okay, so they would have finite, this thing. And the tolerance is based on intended use, whether using only for 3D CRT, non-IMRT, or whether using it for IMRT or for SRS. So when you are using it for SRS, you look at the mechanical, this thing, or all that tolerance is much less. Okay, collimator size indicator, laser localization, etc. Plus X-ray output constancy, irrespective whichever way you're using, you have to be, it has to be good. Electron output constancy has to be, good, within plus minus 3%. So all these parameters are very important. In all, whichever department you are, your physicist, or sometimes some departments have dosimetrists or the RTTs, they will be doing these quality assurance. Most of the times you are there in the department, but you don't really peep in to see what is really happening. Just go and ask them. Just be there. They'll be very happy to tell you what they are doing. And once you see that, you will know that. So again, I have shown only daily checks. I have not shown monthly, weekly, monthly, and yearly checks on that. So that is what you have to read, and go and not just read, ask them. And why do you do this? Does it sometimes vary? Okay. So you please go and speak. For 15 minutes, you will speak to your physicist or dosimetrist. You will learn a lot. Okay. We don't have to go and ask them only about whether this plan is ready or when this plan would be ready. That is obviously you do that. That's one of our business mutual this thing. But this also is important. The machine is theirs and yours, and it is for the patient. So now talking of dose at a point inside the body, or it could be a phantom from a beam in relation to the surface or the reference point, or a Dmax, which is a dose ratio. So these are different dose ratios. You're talking about, suppose, from the surface or Dmax to a point inside the body, or it could be a phantom. Okay. So what we talked about attenuation, now we're talking of its attenuation, which is decreased intensity. As the depth inside the body, the beam travels, density of medium, photon energy, wedges, shielding, tissue compensated ray, all these will cause attenuation of the beam. Okay. Then the scatter of the beam, because beam is also getting scattered. So that depends upon beam energy, field size, and depth inside the tissue, and the intervening material. Scatter also, all these things will impact the scatter. Okay. So as you remember, when there's less beam energy is less, there'll be more scatter. When the field size is more, there'll be more scatter. And the deeper you go inside the tissue, there'll be more scatter. Anything which comes in the way of the beam, it will give rise to increased scatter. So distance from the source is, it is inverse square law. And the percentage depth dose, finally calculate percentage depth dose. The other way is also at percentage depth dose, that means at depth D. Okay. Whatever is your dose to D max, how much it is, that will That is based on all of these factors: attenuation, scatter, and distance. You would say how distance matters. I will show later. And so percentage depth dose increase, that means more of the radiation that you give at surface, or that Dmax is reaching at a cell depth 10 centimeters, it will increase with some things we get intuitively, other things we don't get intuitively. So you have to understand the reason. Once you understand the reason, the next time you would just get it, don't have to remember. First and foremost, it depends upon energy. Okay. So remember when we were talking of all the previous interaction of X-ray with matter, we sort of said that, but when you're talking of basics, you don't pay attention to that. Okay. Now you're talking of percentage depth dose, because something is something that we use. Now suddenly you say, yes, with energy it increases. So energy is the most important factor. So when you are not getting enough PDT, all you ask is, okay, let us go to 10 MB photons or 15 MB photons. So cobalt change to 6 MB. That is the best thing you can do to increase your percentage depth. Then relatively less important thing, but they have an impact, is field size. So now sometimes this, you don't get it intuitively, which field size would have higher percentage depth. Okay. So, large, small field size is good, narrow, sharp beam, that is all right. But so field size, should I tell or no? Okay. Again, you all read and understand. Okay. I don't want to do spoon feeding. Okay. So which field size? So narrow sharp beam or a wide beam? So you all think and get it, which will have a higher percentage depth dose. Then source to surface distance. This is really difficult to understand, conceptualize. Okay. If when you read it, try to think intuitively, you will not get it. On deep thinking, maybe for a day or two, you will get it. Just by thinking and just you draw something, you will not get it. So what happens with SSD? Okay. See, if you have memorized it, just okay, with SSD increasing, what happens? Whatever you have memorized, you're going to forget. In all our life, we memorize so many things, we remember so few things. Okay. So main thing is you derive that why SSD, what will be the impact of SSD on percentage depth dose and why? Not just what will be the effect, not so what will be the effect. Then field shape. So again, these things have relatively minor impact on percentage depth dose, but conceptually you have to understand, because many things, these minor things, then they add up to a major impact. So field shape, from a circular field to a square field to a rectangular field to a long rectangle. In which one it will be more? Then tissue maximum ratio, or TAR, which is used in the SAD when you talked about the source axis distance. One is the SSD treatment. We also call it SSD treatment when it is not at the isocenter. You have not got that center of the target volume at the isocenter. You are given those the field sizes on skin or the surface, and it is what we call the SSD treatment, source skin distance, and there you apply a percentage depth dose chart. But where you're using a isocentric treatment, the isocenter, you bring the isocenter will remain there only. Isocenter will not change. It's a fixed space and fixed point in space. You bring the target volume by bringing the patient up on the couch, moving left, right, center, up and down. You bring the center of the target volume at isocenter. And then when you use the field from whichever side you are using, then the field size is at the isocenter, and the method of calculating those is based on, then you call it the SAD technique, source axis distance, and it is a TMR or TR ratio. And it is based on all this, but it does not consider the inverse square law, because inverse square law, it does not have a fixed distance from different directions. It will be that tumor will be at a different distance. So here I am showing the percentage depth dose. So there are different energies. This is a cobalt 60, this green line, then 6 MV, the black broken line. Then after that, this is 10 MV, which is a solid line, orange line, and then even higher energy. So what you see is these are all mega voltage radiation. Only difference is that the energy is increasing. So, cobalt 60, the energy is 1.25 MV. Now, you all have to read what is the average energy of 6 MV. Is it 6 MV? Is it more? Or is it less? it is less or more, how much more or less it is. That is something you all have to read and figure it out. So in this, you see in all this mega voltage at the surface, the dose is not 100%. Even for cobalt 60, you see surface dose is less than 100%. It is around 80%, or less than little 80%. And as the energy increases, the surface dose has become less, or that means it is becoming less and less. And after that, after it reaches a point, what we call the D max, that means the maximum dose at this particular point, which is either millimeters or centimeters away from the surface, then the dose starts falling off to attenuation, because of attenuation. And it is not a straight line, it is slightly curved, more or less straight line, slightly curved line. And as you say, the beam never becomes zero. These are X-rays, so they will get attenuated. Okay, but it will not disappear. So again, from this oncology medical physics.com, I got this. So this is also known as a build-up region. From the surface to D max is the build-up region, and the maximum dose D max is a term that you all know very well. And there's a fall-off region, and this is composed of, remember what we had shown is the inverse square law. It is distance from source plus the depth in medium, how much it is attenuated, plus the build-up depth in medium. Okay, build-up. All these together makes this one. So what is the percentage depth? Okay, so inverse square law keeps on happening as the distance increases. That becomes very rapid. The contribution of this thing is there, and then attenuation and build-up. And this is not universal. Okay, so this is a percentage depth dose for a given field size in a phantom. If a flat surface, if it is oblique surface, if it is a different shape of the field, different size of the field, obviously different energy, it will change completely. This percentage depth dose will change. So it is not sort of written in stone. You have to know what is the. So isodose charts these days in departments, they are taken out only before exams, or sometimes you are there in the drawer, you out of curiosity to see isodose chart, but they were ubiquitous. Once upon a time, they would be big, fat, leather-bound registers. All the isodose charts will be there. You will just flip them. And when I joined residency many years ago, we used to also do manual planning on these isodose charts, and that makes you think and understand. What I'm trying to do is that you all think. So basically, these are 2D maps of a dose distribution, and they are normalized to the D max. So central axis is important. When a central axis which is aligned to the isocenter of the beam, central axis of the beam. Okay, and that has the highest dose, except sometimes there's a flattening filter. And in some of the isodose, you see that it is not, the 90% is not at the center of central axis, but it is little there because it is overcompensated because of the horn. And build-up as the energy transfer. So what is the cause of the build-up, surface build-up? Okay, the build-up depth that we talked about, this build-up depth, because the electrons that are generated here, they have not yet deposited all the energy. So the range of the electrons is higher and higher energy. So all the energy that is being sort of liberated is not being deposited in that region. And once that reaches the equilibrium, then you get the D max. Okay. Build-up as the energy transferred from the photon beam is initially absorbed by electrons which travel some distance, go further beyond. And this energy is eventually deposited as dose at a deeper depth within the phantom. They're talking of phantom here because that is where we generate the isodose charts, PDD charts. And the build-up region ends when the amount of energy taken downstream by liberated electrons is equal to the energy deposited at that location by electrons liberated upstream. When give and take is equal, and that's what happens, then you reach the build-up D max. Okay, and this condition is known as charge particle equilibrium. That is one. And field edge, and you look at the dose near the field edge, falls very rapidly because there is both geometric penumbra and also there is loss of lateral scatter. So both these contribute that here it is falling off, slowly, and here it is falling off rapidly. But there is a gradient here also. You will see later on we'll talk about penumbra. So the AAPM-TG45 defines actually what is flatness and symmetry. These are looks like they are same, but they are different. Flatness and symmetry. Flatness is basically the ratio of the maximum to minimum dose inside the central 80%. Okay, central 80% of the full width at half maximum. So this FWHM, 80% of this is a central axis, and that's where you see what is the minimum and maximum. Okay, that is the ratio of minimum to maximum, and this is flat. This should be around 3%, less than 3%. Okay, plus minus 3% is acceptable flat. And now symmetry is different. Symmetry is when you are comparing the right side from the left side. So sometimes the beam, you might think, well, beam should be symmetrical, but so many things are happening. The electron is bending, the target is there, all those things. So you have to be sure that the beam is symmetrical. It is flat. So of course you're talking of with a flattening filter. There are FFF mode also, filter flattening filter free mode. We use it different time. We will discuss this when we talk about advanced techniques. So we're talking with the flattening filter. What is the flatness and symmetry that is expected? So teletherapy planning, it went on from 1960, simple 2D planning, then conformal planning, then IMRT with inverse planning, and of course now IGRT and 4D planning. And in terms of the planning aspects, we already talked about simple things, but beam energy, beam placement, beam shaping, and beam modulation. I will tell few important parts before we go to the next part of the 2D and 3D actual planning. So photon beam energy, photon beam divergence increases with, who will tell me? People can write in the YouTube chat also. Increases with. So I am surprised so many people get it wrong. And intuitively they think that, oh, I'm sure it must be increasing with, but it is actually wrong. Beam divergence increases with SSD. Anyone else who says increases with SSD? Okay. So that's why I've drawn this diagram. The breast OPD I've put it. Just imagine the source of electromagnetic radiation, which is very far from here, from Earth, Sun. All the visible light and all that comes from there. In your physics experiments in school, when you have to take a parallel or a light source which was like parallel, we used to take that sunlight, almost like parallel. It is so far. Of course, it will have divergence because of source, but it is so far from here that it has become almost non-divergent. So when the SSD is increased to so much, the divergence becomes so less that cannot be even appreciated. Okay, so what is done here is, so this is a surface, okay, and this is a source. So this one, the SSD is less, then you increase SSD, increase SSD, increase SSD. On skin, field size is same. Okay, on skin or the surface, field size is same, but as you see the SSD increases, there is less divergence. Okay, so there is less divergence. And remember, I was mentioning that it travels in straight line. So simple geometry. You may not know anything. Just take a pen and paper and a scale, ruler, and you draw it, and you will get for yourself. Okay. So and then to remember. So can divergence be completely eliminated from a clinically useful beam? Okay. You can say you can take the machine to the sun, but hardly any rays will reach here. It will not be clinically useful. Or you can increase. Of course, these days very simple methods are there. I will talk about. It can never be eliminated. Okay, you can one part of it. You can half beam block. You can do. Okay, central axis. Okay, one jaw you make 0, but on the other side it is still divergent. You cannot make it like this. So when is a photon beam divergence of special concern? So we have all lived and given radiotherapy accepting there is a divergence of the photon beam, but when it is of a more concern. Okay, so there are situations when is of greater concern. One is when something like brachial plexus is there, a critical organ, where otherwise the beam may have missed it, and we are treating with multiple fields. The divergent, that part may, irradiate from the both beam, multiple fields, and yet. Then where the curvature is increasing, again, it's a very critical. These are organ in series. Okay, so even one part of it is receives much higher dose, then that could cause irreversible and severe late effect. So a divergent beam, two adjacent field divergent beam, if they overlap, you could have a serious consequence of a brachial plexopathy or a radiation myelopathy. So how to manage issues of divergence? The simple fields, again, remember geometry, you may forget the formula. I can't remember the formula, although I've written, but just put a piece of paper, and you should need a piece of clean paper and scale, ruler, or this thing. So how much should be? So earlier when we used to give mantle and inverted Y, we used to do the gap calculation on the simulation, on a 2D simulator. Most of you have not have even seen 2D simulator. So we used to calculate what should be the gap between the mantle and inverted Y field. Or for craniospinal, CSI, if you're not treating on a helical tomography or other machines, there will be, in adults, you will have to give a junction, okay, between, say, dorsal field and the lumbosacral, and then there will be a junction between the cranial fields and the spinal field. So whenever there is a junction, because it is divergent, how much should be the gap or how you should deal with the gap? Okay. Between the cranial field and spinal field, there's a different approach we will discuss later. I'm talking about between two adjacent fields. So this is the SSD, SSD1, SSD2, and this is the length of one field, this is the length of the other field. Basically, you have to see that they will cross each other, because you don't want to keep them very far, otherwise it will miss. You have to see that they cross each other after the critical structure. So the critical structure here is spinal cord. So they don't overlap before the spinal. So this part which is in the overlap field will get dose from both the fields, both the systems. Not a very high dose. I made it a little dramatic by showing more divergence. Divergence won't be so much. So you want to know how much distance you should keep on the surface of the skin between both the fields, so that the intersection of the divergent beam is beyond a certain point. So this depth is D, and so this D would be, so S. So the S separation on the skin, which is what we call the gap calculation, which would be 0.5 L1. 0.5 L1, that means half of this, D upon SSD1. Okay, so D is this and SSD1 is this, plus the same you do for this. Basically, this ratio, this distance, if you look at, is like two triangles. These are two triangles. Ratio of this to this will be same of, so ratio of half L1 to SSD1 would be same as a ratio of S1 to D. So that is how you can easily calculate. If you don't want to calculate, you draw it on that, you will get it. Okay. So this is how it is. So one way was to have a separation or a gap on skin between adjacent field. And still, because some region is getting underdosed, so you would move the junction. So you spread out the cold and hot region or feathering. That is one approach. Or you use a half beam block using asymmetric jaws. Earlier, we used to actually use physical blocks. There used to be breast cones. Some departments might still use it on a cobalt machine. So breast cones were of two types. One were half beam blocks, other were not half beam blocks. So they also made it easy to set up on that, because they would touch on the skin, on the chest wall. And they also cut off the divergent part. So the lung dose was reduced, because the divergent beam will not go into the lung. Okay. But only half the beam you can block. You can't block the full beam. Once you block the full beam, there is no beam. You can't use it. Then half beam block with monoisocentric technique, like in some departments like ours, which we use it for treating two adjacent field from different direction, like for breast and supraclav. And for CSI, again, I am not talking about, but it's very important to understand, even on the department, you may not be using this, but how the couch twist and collimation was used for this thing. Okay. couch twist and collimation, and non-coplanar field to have this. So penumbra, again, now we're talking about what we need to know about a clinically useful beam. So what are the different types of penumbra? I've just drawn it here. So you have a source. Penumbra means where the line, the dose is coming down. So there are different definitions of penumbra, from 80% to 20%, 80% to 10%. Basically, it will never be just rapidly that you have your 90% ISO dose and then it becomes 0% ISO. It will not happen. So there will be a zone. Okay, and there are two sources of penumbra. One is the transmission penumbra. So if suppose your the jaws are like this, some of the beam is not going through the jaws, other beam is going through it, so it will cause a penumbra. Okay, transmission, because when it is transmitting through the jaws. Other is geometric. If you have a big source, a 1.52 centimeter wide source, so from this part it will reach here and this part it will reach here, so you will have a penumbra because of the source, because this has traveled more distance here. Okay, so this will be weaker and this has traveled less distance here. This will be stronger. So you will have a penumbra here. Of course, this geometric penumbra can be reduced with a very small, source size, as small as possible. But remember, in a telecobalt machine, source you cannot make it say 2 millimeter, dia source. So otherwise it will not have that much of radioactivity, which will be clinically useful. Okay, so that is important. So beam, I think this is the last this thing of. So the beam shaping and modifying devices. So I am just mentioning the names. When we will talk about the actual planning, 3D planning or 2D planning, then we will use that. So the shields are, you will see on the Cobalt machine or a Linac, most of the shields are plain this thing, but sometimes you would have a divergent shield, because you know on which machine you are going to use, you know where you are going to keep the shielding tray. And again, as simple as that, the geometry. Okay, suppose your shielding tray is going to be here at this place, and you know how much is the divergence at this point of at that place. So your shields have to be designed that their surface or the divergence of the shield matches with the divergence at that at that height, from distance from the shielding frame. Then shields could be very simple pieces, rectangular or square or pencil shaped pieces you could use for corner blocks or something else. They could be customized and manually. Before multi-leaf collimators were there, it doesn't mean that we were not using customized shields. When we were giving mantle or inverted Y or any other complex shape, we were using customized shields. So with cerebent blocks, we used to make. The mold room was not just making the molds. One of the important duties of mold room, which has now almost gone away, was to make customized shields. Then wedges, coming to the very most important this thing, they have not disappeared. They may have physically disappeared. Even now the machines come with physical wedges, but more and more there'll be virtual wedges, and there were fixed angles of wedges, 15 degrees, 30 degrees, 45 degrees, 60 degrees. But now you could have, once we use, electronic wedges or virtual wedges, you may use 22-degree wedge or, 37-degree wedge, whatever it is. Basically that much of wedge effect. Then universal, sorry for the misspell. Then tissue compensator. Again, I am not sort of showing the tissue compensators. When wedges would compensate for different things, when there was uneven missing tissue in both axes, X, Y, or different direction, then you would use tissue compensators, like typically in the neck, breast, cone, surface. So here you see that this is the bending magnet comes, this hits the target, then there's a flattening filter, and then this is it's monitoring of the dose. And then here there is a wedge, one side is a metal thing, one side is thick, one side is thin. So it causes differential attenuation of the beam. So I think now I will invite our physics colleague. Has she joined? Udita, so just please see. I will stop scaring. One second. I just told her. Has someone joined? Yeah, is joined from. Okay. Udita, you can just camera on.
Am I audible?
Yes,
Sir, I'm audible.
yes, you are on.
Okay. So, shall I share my screen?
Yes, please take 1 minute later. So, yeah, you can. Uh,
Am I audible to all of you?
yes, you are audible and
And my slide are visible.
yes, very much.
So, shall I proceed?
Please.
Uh, shall I start?
Yes, please start.
Yes, sir. Okay. Thank you, sir.
The full screen, yeah.
Yes, sir. So, good evening, everyone. Today, my talk on radiation quantities and unit. Myself, Udita Upreti, medical physicist from TMH, Mumbai. So, we'll discuss today radiation quantities and unit. So, my topic contains our introduction, activity, karma, exposure, absorbed dose, equivalent dose, effective dose. So, first of all, what do you mean by the quantity? Quantity means to characterize a physical phenomena in terms of that are suitable for numerical expression. A physical quantity is a phenomena capable of expression as the product of a number and a unit. So, if we'll see, so many examples are here. If we'll see that 54 kg means there is a number 54 and kg is the unit. So, without a unit, that there is no value of any physical quantity. So, unit is very important part of a physical quantity. So, if we are talking about the radiation units, so first we know about the governing bodies. These are the governing bodies which deal with radiation unit and give recommendation of their uses. So, these are ICRP and ICRU, International Commission on Radiation Protection, International Commission on Radiation Unit. So, International Commission of Radiation Protection dealing with the protection quantities, and these are the independent non-government organization and motive to prevent deterministic effect and reduce the risk of stochastic effect. And similar way, the ICRU is a ICRU play a very crucial role in the field of radiation therapy. It provides the internationally accepted recommendations related to radiation quantities, unit, terminology, measurement procedures, and the reference data. And in order to access, it gives some recommendation about definition, concept, and unit and operations. So these are very important because we are dealing with the radiation sources. So, very basic quantity. First, we will discuss the activity. Before activity, first, just I am refreshing some. What is the radiation? What is the radiation? Radiation is nothing but it is the energy transfer from one place to another in terms of waves and particles. And what is radioactivity? Radioactivity is the property of some atomic nuclei to emit energy and particles spontaneously. So, as we know that radiation sources emitted continuously alpha, beta, gamma rays. So, one of the characteristic is tell about the nature of radioactive source is called the activity. So, it is simply definition is it is the number of radioactive disintegration taking place per unit time. You can see there a number of nuclear transformation taking place in time. So, because this is the uh, related to the radiation field quantities, so the name is given as a becquerel of this unit. SI unit is adopted as a becquerel is its unit. In generally, the unit is 1 by seconds, but To make them separate from the physical quantities, the name is given the greatest scientist, that is the becquerel, and SI unit is termed as a becquerel, and the old unit is the curie. Curie also a very we know very well Madam Curie, and she discovered polonium and radium, and based on that, the activity also is one of the unit of activity. So, what is becquerel and what is curie? Simply in define in one sentence, one becquerel is equal to the one disintegration per second. One becquerel is equal to 1 dps. Simple. But one curie is time taken for 1 gram radiation to decay or disintegrate. So, becquerel as adapted as the SI unit. SI unit means International System of Unit, and curie is a old unit. But both are unit of the radiation activity, and the relation between them is simply 1 curie is equal to 37 gigabecquerel, or 1 millicurie is 37 megabecquerel, like that. So next part is the decay constant and half life. So what is decay constant? These two parameters also related to the radiation source, which we are dealing with the in our daily radiation therapy diagnosis purpose, and nuclear medicine also. So first we should know the characteristic of the radiation sources. For one is the activity, the other is the decay constant and its half life. So decay constant is nothing but it is a simple probability that a nucleus decay in time interval dt. So simple definition, probability that nucleus decay in time interval dt, and quality. This quantity also related with the half life. Half life also very well known things. Then half life is the time taken for a nuclei to decay to half to its initial value, and the relation between decay constant and t half half life is t half is equal to 0.693 divided by lambda. This is the very standard relation between decay constant and half life. So unit is second, or minute, or can be hours. That depends on characteristic of nature of their radiation sources, and SI unit as a second. Now we will tell about discuss about the fluence. So, absorption of energy from X-ray and gamma ray. So, one terminology is called the fluence. Fluence is simply a number of particle passing through a unit cross-sectional area, dA. So, here you can see that one imaginary sphere is there, and this is the cross-sectional area called dA, and this is the point of the measurement. So, where we can find out what is the fluence. So, fluence is number of particle incident on a sphere of cross sectional area dA, and simply the unit is 1 upon meter square, because dn is dn don't have any unit. A is the area will be the meter square or centimeter square, that depends region of interest and volume of interest. Second is flux. Flux is the fluence rate only. If we will divide the fluence with the time, so we will get flux, that means fluence rate, and simply we will add one unit, that is the second inverse. Initially the unit is per meter square, and if we will divide by the time, so second will incorporate here, so the unit will be meter minus 2, and or you can say per meter square per second. Now energy fluence. So there is a little difference between particle fluence and energy fluence. Simply it is the amount of radiation or energy passing through a unit cross sectional area. So it is denoted by the psi, or is equal to dr by da, where the dr is related to the energy, amount of energy, so its unit is a joule, and area is the meter square, so joule per meter square is its unit. So now we will talk about the exposure. Exposure is a very old and very basic quantity of a radiation field, and it is a directly, you can say that it is a amount of radiation measured by the exposure initial days. So as we know that the X-ray and gamma ray cause ionization and produce ion. The number of charged particle produced by ionization is directly proportional to the radiation. So the term exposure refer to the radiation quantity measured in term of ionization in air in a small volume around a point. So it is a measure of ionization produced in air by photon. it is very important part. This is only valid for the photons. ICRU define a very simple definition that it is a quotient of dq by dm, where dq is the absolute value of total charge of ion or one sign produced in air when all the electrons liberated by photons in air of mass dm are completely stopped in air. So that means, according to the definition, when we are measuring the exposure, there should be a charge particle equilibrium condition, that at that time this definition is valid. So SI unit of exposure is coulomb per kg. Special unit of exposure is given in the name of scientist, that is Röntgen, and there is the relation between Röntgen and coulomb per kg is 1 Röntgen is equal to 2.58 into 10 raised to power minus 4 coulomb per kg. And simply this one equation show that 1 Röntgen means 1 electrostatic unit charge liberated in 1 cc cube of 1 cc of the air. So this is the practical setup of the measurement of exposure, and this shaded area represent the volume of interest where we want to measure the exposure, and there should be maintenance of the charge particle equilibrium condition, then the exposure definition should be valid. So, what is the characteristic of exposure? First of all, it measures ionization in air only. It doesn't measure anything for the medium. So, keep in mind this is only valid for the air only, and cannot be used for photon energy greater than 3 MeV because of the increased range of the liberated electrons. So, very difficult to maintain that measurement setup. So, it is valid up to 3 MeV only. Röntgen is the unit of exposure. X or gamma ray only cannot be used for beta ray and neutron. For that, the another unit is called the red, was introduced in 1956, and finally that Röntgen was accepted as a unit of exposure, that is only valid for the air, and that is up to energy up to 3 MeV, and gamma and X-ray only. The other thing can be expressed in terms of red. So now, very important is the karma. Karma is a non-stochastic quantity related to the energy transferred from uncharged particle to matter. So simply, you can see also here, karma is acronym for kinetic energy released per unit mass. So it is denoted by K, dTr by dm, where dTr is the sum of initial kinetic energy of charged particles liberated by indirectly ionization particle in mass dm. So by definition, it is very clear that ETR is the energy, that is the transfer energy, that is a unit is joule, and m is mass, so it is a kg. So joule per kg is the standard unit of the karma, and special name is given by the scientist name, that is the gray. And old unit can be red. So there is a relation also, one gray is equal to 100 red. Now, what are the characteristics of karma? Karma can be defined for any type of material, is defined for indirectly ionizing radiation only photon and neutrons, is the kinetic energy transferred to the secondary particle, that is not necessarily spent in volume dV where they were liberated. They are always deposit their energy in another level, not exactly where they are generated. The medium of interaction of photon must be specified while measuring karma. Now, what is collision karma and radiative karma? Indirectly ionization radiation means there is two-step process always. Energy transfer from uncharged particle may be spent in two way, either collision resulting in ionization or conversion to photon, or both. So measure of the part of initial kinetic energy of electron in low atomic number material is expended in inelastic collision with atomic electrons, but only a few part, only a small part can be interact with the atomic nuclei, and it will it will generate a bremsstrahlung radiation. So whatever the energy transferred from the uncharged particle to charged particle, that is the sum of the these two karma, that is the K collision and radiation, K radiative. So the total karma is represented as a K collision plus K radiative. So this is the mathematical indication, mathematical expression to express the karma in terms of fluence. So if energy of the photon, incoming photon, is multiplied by the mu tr by rho, this is the and a mass energy transfer coefficient, so it will tell about the karma. And K collision, that is multiplied by the mass energy absorption coefficient multiplied by the incoming photon energy, so it will represent the K collision. And because there is some losses of the radiative losses, the bremsstrahlung radiation, so the final equation of the karma, with the total karma, will be expressed in terms of K collision is equal to K 1 minus G, where G is the energy fraction lost to the radiation process. Now we will tell about the karma and exposure. So the relationship between exposure and K collision can be expressed in term of the measurable quantity. For that, first we should know what is the mean energy. So mean energy is nothing but it is the energy which which is required to produce ionization in air. So per ion pair producing energy required 34 electron volt in air. So some reference book it is given by W by E also. Here I have put W bar like that. So it is ratio of delta E by delta N, where delta E is the sum of kinetic energy of electron spent in ionization and excitation. N is the sum of ion pair produced by the secondary electron in the air after the interaction. So when we will deal with these two equations, we will get the relation between karma and exposure. K collision karma is the multiplication of mean energy, mean ionization energy and exposure. So now the another term is the dose. So initially, in early days, the amount of radiation absorbed was estimated by reddening of human skin. So that dose is known as the skin erythema dose. But what is the drawback of that? Skin erythema depends on the skin type, quality of radiation, extent of skin exposed, dose of fractionation. So there is no uniformity to express the skin erythema dose. So dose concept came into the picture. So now the absorbed dose is quantity used to measure the amount of ionization radiation. It is a measure of biological significant effect produced by ionizing radiation. That means we will tell about just like 1 gram, what will be the effect. Like that, it will tell about the biological significant effect if we know the value. So it is defined as the ratio of dE by dm, where dE is the expectation value of energy imparted by any ionizing radiation to the matter of mass dm, and its unit is the same as a karma, and a special name is the gray. The difference I will tell you the karma and dose in next slides. So the knowledge of radiation fluence in the volume of interest, including scattered radiation, is necessary for the calculation of absorbed dose. So there is the relation between the previous unit red, 1 gray is equal to 100 red. And now I kept this slice to make you understand what is exactly karma and what is exactly absorbed dose. So to understand very clearly this thing, karma and absorbed dose are related to the quantification of interaction of radiation with the matter. So karma in any volume V is the place where energy is transferred from uncharged to charged particle. The absorbed dose is in any volume V is the place where kinetic energy of charged particle is spent. So there is the difference, I think is very clear. First part is the transfer, second part is the spent. So in combinedly, if we'll say that the charged particle entering V any volume V, contribute to absorbed dose but not to karma. Charged particle liberated by photon in V may leave it, carrying away a part of kinetic energy. This energy is included in karma but not in absorbed dose. Now, the relation between absorbed dose and karma is represented by this graph beautiful way. So you can see here, this is the depth, and the y side it is the absorbed dose and karma. So karma will be the maximum at the surface and reduces with the depth, because in the first layer, if we'll see at surface level, the karma will transfer its higher energy to the secondary charge particle. At that time, those will not uh, absorb at the same level. It will create the build-up region from the next level. So at that time, it will start. The dose build-up will start and karma will reduces. At some time, some point, at any depth, when they are exactly equal to each other, that condition is called charge particle equilibrium condition. In practically, it will not happen. So you will see after some time, it is parallelly decrease with the depth. So karma and d will be parallelly decrease with that after getting a build up region maximum level. So there is, you can say, in the beta is the ratio of absorbed dose to the collision karma. And if beta is equal to 1, when absorbed dose equal to the karma at the state of equilibrium. In build-up region, b less than 1, this is the build-up region. And the second reason, when d will be more than the karma, it is called the transient equilibrium region. Now I will come to the protection quantities, that is the equivalent dose. Equivalent dose is the product of absorbed dose, average over the tissue or organ, and radiation weighting factor WR selected for type and energy of radiation involved. Because we know that there are the different type of radiation, and they are having different impact on the tissue. They are not uniform effect on the tissue. So it is very important to know which type of radiation is dealing with the a tissue. So that comes as a equivalent dose, absorbed dose multiplied by the radiation weighting factor. Conventional unit is RAM, but the SI unit is Sievert. So this is the radiation factor weighting factor chart for photon. With respect to photon, uh, how much harmful the other charge particle or radiation, you can see there. Like if we are using the proton or charge particle is twice of the photon beam, and if alpha particle, that is a 20 times of that. So that's why it is important to calculate the equivalent dose. We have to multiply by the radiation weighting factor. Now this is a very important effective dose. So effective dose is the product of equivalent dose and tissue weighting factor. Simply, our tissue doesn't have the same sensitivity towards to the radiation. So each tissue is given a factor based on response to the radiation, and this factor is called tissue weighting factor. So effective dose will be the multiplication of the absorbed dose, radiation weighting factor, and tissue weighting factor also. Its unit is SI. SI unit is Sievert. So you can see the reference of ICRP 103. There is the different of tissue and different sensitivity towards to the radiation, and you can see here that bone, surface, skin, they are having very less sensitivity as compared to other organs. So this is what we have in this slide, what we have studied, that activity, exposure, absorbed dose, equivalent dose, and effective dose. So this is the pictorial representation, and this is the summary of my topic today. So exposure, these are the doses, these are the conventional unit red and RAM, SI unit gray, and Sievert. Sievert is the radiation protection quantities. So this is all summary of today's lecture. quantity, name, symbol, unit, and year, and SI system. This is the SI system. I have written here wrong. This is the SI. So exposure, absorbed dose, and some of these are non-SI systems. So thank you. These are the references. Thank you for your patience.
Okay, thank you. Rita, can you stop sharing your screen?
Okay, sir.
So thank you very much for all the students. I know this looks little hi-fi karma rate, air karma, and collision karma, but these are important. You have to know that to understand, both for brachytherapy and teletherapy. And thank you very much, Udita. And in the next weekend session that we will be having, not next weekend, there'll be more of physics. This time I had kept it simple so that you don't run away from physics. Okay, I didn't
Okay.
want to scare you all. So thank you, Udita. And
Thank you, sir.
now I have our director academics, Dr. Banavli. He is a pediatric medical oncologist, but an educator, very passionate. And he has, thank you, Udita. Yeah,
Thank you, sir.
thank you, thank you. So, Dr. Banavli, I want him to tell the students, and this is a lot of patients, people have registered for him. Patients. Wow. More than 1,500 people have registered. Some are few hundred are watching it live on YouTube. Others will watch it live on YouTube. I know, watch it on YouTube later. So I have requested Dr. Banavli to tell us a little bit about the educational programs of Tata Memorial Center, about HBNI. We also have a PhD program. There are some PhD students also who are joining even today for physics. I think from BRC people have come here today for physics. So about the health science PhD program also. So Dr. Banavli.
Yeah, good afternoon, everyone. And sorry, I'm late because we had it's still ongoing. Actually, there's a Chintan Shivir in TIFR of the DAE group of all the institutions. So we were part of that. But welcome to this on behalf of administration. I'll welcome you all for this hybrid program, which is very odd actually for somebody like me when I first saw, physics, genetics, and radiobiology. So different fields, but I think looking at the number of registrations, it just shows that how much need is there of such hybrid programs, and that's what was discussed even today in the Chintan Shivir, that there has to be interactive programs, and when we do something just one-sided, that doesn't help in today's world, especially with the new education policy. There's a lot of stress on doing such interactive and hybrid programs. So thank you, Dr. Saeed, for really opening up this hybrid program. But talking about the education at the Tata Memorial Center, as you all know, many of you are part of Tata Memorial, at least those who are here are part of Tata Memorial Center. And Tata Memorial Center stands on three pillars, basically, which is, service is there always. First is service, but along with service, we also take pride in imparting education and doing research. So, and now public health. So, that actually there are four pillars of service, education, research, and public health. So, all these four pillars are on which the Tata Memorial Institution stands. And education is very important because, as you know, sometime back, especially now, there are many institutions, but sometime back, more than 50, 60%, or even 70% of those people who are working in the field of oncology were trained from this institution. But now there are many, many more institutions also. But still, Tata Memorial actually does a holistic work in training not only students in the field of medical this thing, but also the other paramedical and like physics, radio physics, and other technical courses also. And again, like Dr. Sarin mentioned, it's a PhD is one of our important areas that we work. So basically, it's a very holistic type of education that is given here. And in many of you, at least I saw the registration and many of you are MD, MD, so basically MD, DNB. So in this, in the medical side, so for those who are listening from other places, actually we have a broad specialty program in radiation oncology. So that's MD radiation oncology is there. But along with the MD program, we also take pride in conducting or doing, giving other training in the other areas also. So there is anywhere from somebody who can come for observation in for a month or a week or 3 months. But other than that, we also do clinical Actually, there's a clinical training post also, which is for 6 months, and we have various fellowships also in the field of radiation oncology. So those are also there. Along with that, people and so many of I saw the registrations. Many of you are not even from India, well, from out of India, especially Bangladesh and all. So we also give training to those who are in the field of radiation oncology from other countries also. So there are various fellowship, and all this is given on the our website. So if you go to the TMC website and open the training or observers form, there are all these courses which are given. So basically, you can do those, do any training in that. And for those in India, especially those who have done their MD in radiation oncology, we also give SR posts. So SR posts are also there. Do they have few? But they are there. But one thing is important, because up till now, Tata Memorial Hospital and ECTRAC was the only place where we did this. But now, along with Tata and ECTRAC, we also have seven hours, at least four other institutions where we are giving imparting MD radiation oncology. So even in those centers, you can apply and get the SR post if anyone is interested in that. The SR posts are there, training is there, so all that can be done. So another aspect is Tata Memorial Hospital and the extract comes under the remit of Homi Bhabha National Institute, HBNI, what we call it. This is a DAE deemed university under the DAE, which has part of nearly 13 other constituent institutions, different institutions, which are all under the DAE umbrella, are part of this. So we come under the HBNI university, and basically HBNI university is ranked 13th in the country in various universities, and 15th in research. So it's a good university. Lot of research occurs here. Lot of basically publications are there. So we are one of the good universities in the country. So that is there. And now along with Tata and ECTRAC, even our Varanasi centers have come under the gamut of HBNI University. And slowly we are trying to take all the other units of TMC under the umbrella of HBNI. So we will be under one umbrella, that is the HBNI university. So that's one thing. And the other part, actually, along with that, especially for PA students who are interested in researches, we also have both life PhDs in life science as well as health science. So this is another area for especially of those students who are from Tata Memorial Center, it's a hospital, and ECTRAC itself. We also have a MD PhD program. I think the first years may not know, but we also run a MD PhD program. So some of you who are interested in doing pursuing along with your MD a PhD also, so they can catch Dr. Sareen. But we also have a MD PhD program running in this institution. So that's another area where you can basically take part. So lot of opportunities, and some of you who have finished MD who want to join as a consultant also, I think along with Tata, we always keep on advertising our post from other 6, 7 other centers. That is, we have two in Varanasi, we have two in Punjab, we have one in Guwahati, that is in Assam, one in Vishakhapatnam, one in Muzaffarpur. So a lot of other centers are also there where the openings for consultants also keeps on coming. So those who are few who are interested in also being part of the consultant, that is our TMH or TMC family, are also invited to please look into it and please apply as and when the post gets opened up. So lot of opportunity not only for training but also for serving, which is I think the one of the main areas where TMC works in. So I think this next 2 days have a great today and tomorrow. Actually, this course looks and very good, and I think Dr. Sarin mentioned it. This is going to continue every few 2 months or so. This keeps on going. So I think have a great, because education is the best way, and learning is best way of teaching is best way of learning also. So I think have a great this thing. And I think one thing that we miss in India especially is we don't teach students to ask questions. I think hopefully that is not. Sarin is a great teacher, so we will do that. But please ask questions. Unless you ask questions, doubts don't get cleared. So not only we don't need to do didactic lectures at this level, also need to understand the subject. So please ask questions also, and you know think about if any research and all that they were interested. I think a lot of opportunity to research here in this place. So I think that's another thing which I forgot to tell is Dr. Sarin, Dr. Jayant Gowda, Dr. Tejpal, they're an excellent radiobiology lab also. Yeah, Dr. Sarin must have mentioned to you, but that's another opportunity. Always you don't have to learn to get degrees. That is important, but sometimes when you do something, it is out of your interest, your passion also. So I think this is a great opportunity for radiation oncologists to do research in radiation biology. And I always tell Dr. Sarin, this is my question. I'm a medical oncologist, like he told, but I worked at pediatric center in St. Jude's, that is in USA, where one of the Dr. Larry Kahn was there, who did one of the initial radiobiology experiments. And I don't know, for last 50 years, why is it that still you'll give 180 centigrade of radiation every day from day 1 to day 30, which goes on for 6 weeks, 8 weeks. We don't do that. In medical oncology, we give chemotherapy doses. For induction, we have low dose. When we do consolidation, we give high dose because the biology of the tumor keeps on changing. And I have this question always I ask Dr. Sarin, is why is it you all do that radiation in the same dose from doesn't work, the tumor will not follow their radiation biology, it will follow its own biology and it's entirely different. So I think a lot of research needs to be done in that, so I personally feel that this is one area, but the other CT, chemotherapy, radiation that will give, again the same thing. Either you give 3 weekly cisplatinum or you give weekly cisplatinum. My thinking is always that start with 3 weekly, give one dose, let the dose of cisplatinum build in the tissue, then give weekly so that toxicity is reduced. But nobody does that. So I think there are a lot of areas of research which need to be explored. So young mind, think about doing research also not for degree but just for the fun of it. And there's a great opportunity for you all to work with Dr. Sarin and his team in ECTREX. So I think that's one of the good radiobiology labs, I think, or maybe one of the only one in the country. So have a great learning experience for the next 2 days and for the months to come. So thank you, Dr. Sarin, again for doing this. And actually, I forgot to tell, we have submitted that, but he's also starting a cancer genetics program, which is a fellowship, HBNI fellowship, and hopefully even an DM program in cancer genetics. So a lot of more exciting things to come. So keep in touch with Dr. Sarin and enjoy the education. Thank you. Thank you. Any questions regarding education? Anyone has doubts? Anything? Please catch it, Dr. Sarin, or ask it now.
You want to ask now?
No, we teach our students not to ask questions. That's really, go to US, go anywhere outside. Anyone will keep on asking you questions. But here we don't teach. Right from our school days, we are told whatever the teacher says is right, and don't question the teacher. So, thank you very much.
Thank you, Dr. Banavli. That was really very encouraging. So he just, mentioned some of the things. We have a very big educational program, both at MD, PhD, and MD, PhD, and so many things. So thank you very much. Okay. So now it is already 6. So I'll just tell you what So there's a lot of physics in one day. I think it must be all we get physically tired, literally in the literal sense. Okay. I don't know how people run the entire crash course of entire physics. That's not really possible. Okay. What I will do is I will not take full 1 hour lecture. I will full screen, make it full. Okay. Okay. So this is the principles of 2D and 3D radiotherapy. Now what we do as doctors, we go to the physicist. I mean, sometimes as trainees, you think your job is to make sure patient has been simulated in the way that patient should have been simulated. Imaging has been obtained. Imaging is okay without artifacts. The field of vision, everything is covered. And then you draw contour of the body, of the critical structures of the tumor. And if the consultant or more experienced radiation oncologist approved it, your job is done. You tell broadly whether it is palliative 2D or 3D CRT or IMRT, or if it is IMRT, what dose, what organs or what tumor should get how much dose, the PTV, which organs, and that is done. But finally, when a physicist makes a plan, whether it's a 3D CRT or a IMRT plan, then you are only supposed to look at it and agree or disagree with that. Okay. Physicist will tell you this is the best plan, and then sometimes you tell, okay, can we improve it? So if you have to know what are the reasons. Okay. So when you say when a plan, radiation plan is not good or not optimal, that means the areas which you wanted to get a certain dose is not getting that certain dose. Parts of it, that area, or your planning target volume are not being covered by that dose. They're getting underdosed. Or certain organs, normal tissues are getting more than the acceptable or the tolerance doses, okay, or the maximum dose or the volume of that dose, and you're not happy. So when you see a plan, you have to know, even in IMRT plan, you can figure out why this plan. Of course, in VMAT, it is difficult to figure it out yourself that why this area is not getting. But if it is not a VMAT plan, fixed field IMRT, then also you can, looking at the plan from where the beams are coming, what is the weightage of that beam, how the beam is, especially when a 3D CRT, certainly you can make it out that why this is not being covered or why this organ or this part of this organ is getting more dose. And that comes through concepts. And once you understand that why this area is getting underdosed or getting hot, this thing, once you understand that, there is a possibility you may be able to overcome that. Sometimes even after you've understood why this area is getting more or why this area is getting less, you are still not able to compensate for that. But I think that lack of understanding makes you cripple. You are just basically, you just ask, can you make it better? I mean, how will the physicists make it better? And sometimes the physicists also, because now the next generation of physicists, they'll be trained only in IMRT. So they will also not sort of understand how the different beams are interplaying. Ultimately, it's the intersection of the beams. And all that we heard today earlier is the interaction of X-rays with matter. And on top of it is interaction of beams. So multiple fields when are there. So how it's a resultant dose distribution. What happens when there are multiple radiation fields? Okay. So what I will do is just show some of the initial sections of this talk. And then after that, there is a YouTube video link. My last year I had given a year or two before on 2D and 3D. So you all listen to that. And then we will have an interactive section. Okay, it got an hour-long video, and I don't think none of you have energies, and certainly I also don't have. Tomorrow also I have to speak for 1.5, 2 hours. So I will share the link of that YouTube video, and you please watch that. It's on the same link YouTube. So we have talked about how the evolution of planning and delivery. So why it is not moving? I think we already talked about this slide I've shown, using beams of ionizing radiation to kill cancer. So the beams that can be shaped and given from a direction that we want. You know who this person is, Messi, and this is someone has drawn for a child, who was to be treated for a brain tumor. The orbit you have drawn, and we do dose painting. So ultimately, that is what we have to learn, as how you can paint a dose which you want on the area that you want. That means your PTV gets this much dose, and the area that you do not want should not get that much dose. So painting dose. So dose painting, when this concept was new, so it was that. So actually, there is a paper on this. Art of radiation. So this is dose painting. This is, I think, someone's PhD thesis. You can see this universal man in this. You can, with different doses you can paint. So once you decide to give external beam radiation, we're not talking of brachytherapy at all. So you have to see whether it is palliative or radiation. That's the most important distinction, because the technique and approach that you use is important. So palliative means you do not expect patient to live long enough to have serious late effect, but at the same time you cannot ignore the acute toxicity which a patient may have. Okay. So, and in this generally, I've used EQD2 of around 40 grain 20. Could be less, could be more or less, slightly more. So when you give, basically it could be palliative, it could also be sometimes high dose or low or medium. Okay, so palliative radiotherapy is not just 8 grade single fraction. What is the life expectancy? Some patients may be on palliative treatment, but they may be expected to live, say, 1.5 years. Others may have life expectancy of basically 6 weeks or 8 weeks. Okay. What are the other competing health problems, logistics, the site that you want to irradiate, what are the ORs for that, and what is the expected? You focus more on acute and subacute toxicity, and sometimes whom you expect to live a little longer, also the late toxicity. And in the curative radiotherapy, I'm not getting into detail, there's so many more considerations. Okay, that starts from the age to what should be the fractionation, everything you have to take into account. So completely individualized. So of course, doesn't mean that for palliative radiotherapy it need not be individualized. The volumes are highly individualized. Actually, in curative radiotherapy, volumes are more protocolized, whereas in palliative radiotherapy, volumes are much more individualized. No two patients with the same palliative treatment would have the same volume. Okay. Then the planning, before we go to put the beams, there are other things which matter. So the complexity and the technique that we use is on patient anatomy, body size, body shape, internal. Okay, all these are factors which are very important, and this is before you actually take up the patient for planning. Many of these things you would know that. Most patients who come to us, of course, we look at them, we see how they're obese or thin or they're very skinny. We also have their cross-sectional imaging done for diagnostic purpose. So we also get an idea about the internal organ. Okay. Then from the stage that we have, we already know what it will be my target volume expected to be. You do not know that only after you have done the contouring. Even before that, you know, for this patient, this tumor, this is what the location, size, and shape of my target volume is going to be. May vary little bit here and there, and how close it is to the normal organ, how close that will be to the rectum, it will be abutting or sort of going into the rectum, it will be close to the heart or close to the brain stem or lens. So all those things you know in advance. Okay, that will not become as a surprise only when you draw your contours of the tumor and the and then what for that kind of tumor, whether you're talking of microscopic disease or gross disease or radiotherapy only or potentiated by chemotherapy, what is the total equivalent dose and with dose per fraction you want to give? And then under those circumstances, what would be the expected and acceptable, both what is accepted and expected and acceptable acute, subacute, and late toxicity with the dose and fractionation that you want to give, and for different volumes. So you have some leeway in that, because ultimately in the planning that you don't go back and then rework. So when the moment you see the patient, you know the disease, you see the scan, your mind is sort of working through that. You don't sort of go back after the plan is made. Okay? You get a plan made according to, and that's why it is very important. Otherwise, you just do a scan and give it to a physicist. Physicists can make a plan. There are contouring guidelines. There are, of course, as I mentioned earlier, it is a matter of time when AI will do all the contouring. Of course, definitely normal tissues, the body, and even tumor, contouring them. And then we cannot ignore the fact that how much time it is going to take in the planning, then during the treatment, the human resources and the money that will be required. And that could be justified for that course of radiotherapy for the patient consulting on. Okay? You can't say, I mean, out of interest or as part of your thesis, you might do anything, one or two cases. But when you're talking about a department, what you are going to do, everything has to justify, and that is very important. Okay? So this you have to keep in mind, and that's very important. These are general points I'm just making. I mean, it is common sense, but unfortunately, common sense goes for a toss so often that people forget it, and then someone has to tell them that this is how, why you are doing this, and this is very important. You should. So what I will discuss in this thing will be basically simple 2D or a simple 3D RT planning. Mind you, when I'm describing 3D RT, you could have a very complex 3D CRT plan. Okay? Sometimes a complex 3D RT plan, to make it is more difficult than making a VMAT plan or a MRT plan. Okay? So you all have not sort of, those are the cases where we immediately switch to IMRT. Okay? Try making a plan for paranasal sinus or something else or some other kind with a complex 3D CRT. You put, so it could be very difficult. So the simple 2D and 3D RT plans are mostly in palliative setting, but also in curative RT if more complex treatment is not useful or increases the integral dose. So every time, just because it is curative doesn't mean that you need a complex 3D CRT plan or MRT. Because if remember in the previous slide I said, if you're adding any complexity in the entire planning process or delivery process, it should be justified. You should be getting something out of it, not just because it is curative means it has to be IMRT or a complex 3D CRT. And then when you have a simple 2D or a 3D plan, generally the positioning embolization is simple, and the planning you have a wider margins. Whereas when you're talking of more high 3D complex 3D CRT or IMRT plans, then the planning and immobilization as required, it would be very stringent, and you require tighter margins. Sometimes you require 4D CT and image fusion, etc., etc. And for the 2D and simple 3D, you can treat on a cobalt with a shielding tray or any LINAC plus minus shielding tray plus minus MLC. Some centers in the country still have a LINAC which is functioning, isocentric, do not have MLC, but they can use customized block. Most of the IMRT treatment that have come out They were in the era when they were customized blocks. Those days there were two types of IMR. When you used to make various blocks or this thing MLC. Then field verification is very important, and in simple plans you can even do a field based of hotel marking or skin plus minus some imaging bony landmarks you can do. But when you are going to do a complex 3D CRT or MRT, then you treat with high-end Linux, and image verification is must, treatment verification. Otherwise, you do not know. Remember, when we're talking about the the tolerance for different kind of Linux tolerance, the daily checks, depending on the intended use, the tolerance for many of those aspects were different. The same is true for image verification in the planning. So I will not go into details of this, just suffice to say, know your patient, machine, and department. Machine, all we know. Machine, you have to, why I'm talking about, sometimes the QA that is done on the machine, it could be different in your department. The terminology that they use, sometimes they're historical. And many very famous hospitals, their physics departments are so good. They are convinced that is how they should be doing and reporting in their own department. So when you are working in a department, it is very important you should know what your physicists, dosimetrists do daily, what they record, what are the parameters that they incorporate in planning, what is not incorporated in planning. It might look very trivial because everything is standardized, no matter where you're working, doesn't matter. This is one area where wherever you are working, if you go to a new job, many of you will be changing jobs, you should know what they do, especially if it's an old established department. If it's everything is new, and even a new department, because people will carry their legacy wherever they are working, they will bring and use their practices. Sometimes two different physicists, talk differently. So it is very important that you are in sync with that. And one point I've written: techniques used commonly and less commonly, or never used till date. Whenever you introduce a fancy technique which has not been used or was used only 3 times in the last 1 year, different physicists were involved in the planning and doctor. These are the chances of so many things which may, no one may be aware. This is an issue which comes in the planning or the delivery or this execution. Anything which has been done 100 times or 500 times, all the issues which are related problems, technical problems, the dosimetric problems or execution problems, by that time the fifth 500 patient is being taken, you would already know about it. The chances of making a serious error would be less. The last point is about systematic errors and the immobilization devices. You should know in your department, in a curative setting, when you are treating a fit adult, say for head and neck cancer or for pelvis or for a limb, how much setup errors happen. If you do not know, if you read in a textbook or a paper published from MD Anderson or from London, it has nothing to do with your patient. You should know what you are. It depends upon how careful everyone is, how the planning is done, how good are your technologies. So these are some of the things I've just listed out. We're talking of single fraction versus multifractionated, multifraction, interfraction, intrafraction, internal organ movement. This, I have to write it on a slide because people ignore it. The position should be as comfortable as possible. Sometimes when we are setting up the patient, that is the most important point. Can you imagine a neurosurgeon or an orthopedic doing a surgery, complex surgery, and the patient is not in the exact position he or she wants? Okay, in middle halfway through the surgery, either they will not be able to do the surgery or they will just blow their top. That no, why the patient is like this? We underestimate the importance of the ideal position. Sometimes the ideal position is not possible. What is an acceptable position and what is unacceptable position? So many times, just because the position is not correct, you end up making struggle through the planning, and still some parts of the organ or some normal organs or vital organs get more than the desired dose. Okay, So that is very important. And you alter the neutral position only if it significantly helps the planning and delivery. If it is not helping the planning or delivery, you do not change, because the moment it is uncomfortable, that patient is likely to move. You will give a wider margin. So the whole purpose is defeated. Okay, so that is very important, and you make sure that patients are, they're all points where they feel distress, they are well supported. Patient is not in pain or physical or psychological distress. Sometimes it is psychological distress, and your departmental data on random and setup error. Uh, Using that position and immobilization device, and if it is a typical patient, or you expect a greater uncertainty from the patient. So these are, looks like very simple. All of us know about it, but in practice, these are not followed. And because these are not followed, all the wonderful fancy machines which cost millions of dollars, which you have bought, your department has bought for you, you are not able to use it well, because this aspect, and this only a radiation oncologist. In some countries where the technologists, RTT radiographers, they are closely involved in the positioning, they would do it better because they just focus on this. Most countries, it's the radiation oncologists who would do that, at least in India. So if you do not pay attention to this, you will not really doing the good thing for the patient. So so the fields, single photon fields used only in palliative. I would not say only, sometimes, of course, I'm talking of photon fields. Electron field is different thing. And sometimes in radical or adjuvant radiotherapy that we will discuss, I think in the video that you will see patient position. It is not just comfortable, optimal for the beam entry and exit and the organs in between. Because these days you have cross-sectional imaging, so you know if this beam will go from here, where it will come out, and what are the things in between. Okay, that is very important. Then know the attenuation, absorption, and scatter. Again, coming back to the basics of different energy photon beams in different body tissues. So you have soft tissues, lung where there is increased transmission, air cavities, and dense bones. Okay, so there are different types of bones. So that also you have to be certain. Then most important thing which modern radiotherapy is, we, although because we feel that we are using skin sparing radiation, we have come to ignore skin toxins. Once in a while, some patient get moist desquamation, then we start wondering why did this patient get a moist desquamation? And more often than not, we come out with a reason to blame the patient. Patient might have scratched or used this thing or that thing or more tight clothes. That's why this patient. So this is a patient getting moist skin desquamation, which you had not predicted at the beginning of radiotherapy, is a direct reflection on your lack of confidence. Okay? Unsuspected, very few patients have this thing. So it is because either you had not seen the patient, in the treatment position, immobilization was not correct, and very often it is the skin dose, which is because of the skin fold. Sometimes it is because of oblique incident. Sometimes the bolus effect. But that you would know, skin fold is something which is grossly underestimated. Okay, the impact of that. So the energy, and when you are young, you always feel that you drive at a very high speed, you will reach faster or you will be better. There's a recent case, you know that. So there's an optimal speed and an optimal energy. Beyond that optimal energy, it is counterproductive. Okay, so that will depend upon the size. It has to reach the depth, it has to reach, how many beams are required, the intersection of the beam, the skin dose, subcutaneous dose, exit dose. So don't forget that a 10 MV beam, the exit dose is very substantial. If the surface of the skin on the exit side is only 10 centimeter from the entrance side, the exit dose could be higher than the entrance dose. We sometimes just forget because we're only focusing. Okay? So that is very important. So direction is very important. So the entry point, where it will enter, where it will exit, and the direction. So this is again the treatment planning. When you say put the beam, so many things it is already sorted out. Okay, if it is chest wall, to tangential. If it is head and neck, bilateral, and this to oblique. But how did this come about? Because there'll be other sites which will be coming in a palliative setting or a curative setting where you will have to apply and decide from where to angle the beam. Okay, and then finally use the physics logic. Physics logic we will come in planning later, and the anatomy to decide the beam arrangement. So it could be parallel opposed, anterolateral, posterolateral, obliques, 3-field, 4-field. And I'm talking about simple 3D or a 2D plan. And you modulate the beam as if required. Okay, I won't go into these details. The machine you choose, the simulation, that's all right. I think I will not go into the details. In the video that you will see, okay, I'll just this because when you will see the video, you will not get it intuitively. So I'll just explaining how I have made this cartoon. So this is one anterior field. This is I've just taken the body or the phantom as a box. Anterior field, highest dose is at surface. Let us say 100 is at Dmax, and the lowest at certain depth it is 60%. Of course, these lines will not be at equal distance as the distance keep on for PDD. The distance between 60 and 70 will be more than between 100 and 90. But here, just for representation, I've so that to make it in square grid, so I've put them equal distance. So anterior beam. At Dmax 100% and 90, 80, 70. Okay. So in that case, you will see because there is a and the center of these boxes, let us say voxel, I've taken average of 190, so 95, then 85, 75, 60. Okay. So this is there. If suppose it was a palliative setting and you were treating a tumor which is say up to this depth, it was getting somewhere around 85 to 90%. And this exit dose, you are not really much bothered about it. You will use it for palliative setting, what we call single posterior field for spine or something else. Job done. Okay. Then I am adding a posterior field. So posterior field is coming again, and this is I'm talking of SSD method. SAD method will not vary too much, but just approximately for ease of this thing. So here it is 100, 90, 80, 70, 60. Okay. So what will happen to the dose? So the anterior field is giving highest here in this box. The highest is from anterior field 95% AP field, and PA it is getting 65. So total is 160. Here also it is same thing. In this here also AP is getting 75. Here it is 85, 160. So you see that in a APPA field, if the separation is not beyond a certain interfield separation is not beyond a certain thing. Like suppose you are treating a 14 centimeter interfield separation on a 6 MV photon. After the skin, after the build-up dose, everything will get more or less smooth. Okay, so this is how you do it. Okay, now this I have explained because when you will see the video, you will see this graph. So that I'm just explaining how it has been formed. So you will see consequences of higher interfield separation. So when the interfield separation is more, okay, like I gave an example of 14 centimeter interfield separation for a 6 MV photon. If it was say cobalt 60 and interfield separation is 20 centimeter, or 6 MV photons with interfield separation of say 24 centimeter. So then you would see certain things happening. Okay. So first of all, anterior and posteriorly, you will see slabs of hotspots. It could be as high as 120%, which could give rise to subcutaneous fibrosis. Like a cobalt, you treat at 22 centimeter separation, prescribed at midplane with APPA, telecobalt field, you will see thick induration or subcutaneous fibrosis because that area is getting 115 to 120%. So if you give 50 gray in 25 fraction to the midplane, that region is getting close to 60 gray in 25 fraction. Not only total dose is increased, dose per fraction is also increased. Okay. So the solution could be you adjust increase energy. Instead of cobalt, you use a 10 MV photon. or you use a 4-field box or a 3-field box. Then the other thing is central constriction of the 94% ISO dose could be as much as 4 centimeter on either side. So depend upon how much is the interfield suppression, what is the energy. So what we call is a central constriction or a R glass appearance. The R glass is not like typical, so such a true R glass means some central constriction. So you should know which patients this would be clinically relevant. It might be, may say, underdosing the nodes on the pelvic side wall. And what is the solution? Either increase energy, increase the width of the field so that 95% isodose is covering that, or use a 4-field box on this. I think these are some examples. I will now come to just show this. When you see the video, you understand. So here what is happening, there's one anterior field there, 100% to 60%. Now I have added a right lateral field, which is coming from there, anterior, and yeah, this was the anterior, and this right lateral field has come. So right lateral, because it is coming from right side, so at surface 100%, then 90, 80, 70, 60. Sorry, it is written the other way around. I have to just flip it. Okay. So now you have to see the grid and what will be the dose in that grid, and that is very important for you to understand how you will use wedges and where will be the ultimately. When you think of a plan, you should immediately come to you within as an intuitive. In this plan, this is the area where you will have a hot spot, this is the area where you will have a cold spot. Any beam arrangement you see in a flash, it should occur to you. In this, when you put two beams like this in this body shape, where will be the hot areas, where will be the cold areas? You should not take 1 minute to ponder and think and get it right. Okay? Because I'm talking of hot means it is getting 120, 110, 120%. Cold means it is getting 80%, 70%. So just simple knowing which beam arrangement, what shape, external shape, where will be the cold spot and hot. So this is how to understand. So in this, what will happen? So where will be the hot spot? Where will be the cold spot? Looking at this, so I've just again computed these values. So this area, this box is getting 95 and 95 from both, getting 190. And the other corner, because the beam has attenuated further, remember the attenuation of beam, all that we talked about. As the beam goes through the tissues, it gets attenuation. So that percentage depth dose is just the attenuation, scatter, and inverse square root. All contribute to it. So all of them have happened. This is farther away from the source. It is more sort of scattered by that region, and it has gone through so much of tissue. So that's why it is attenuated on both from both the beams. So that's why you see, if suppose the central dose is around 165 in this center, this is getting 190. This is getting 150. So now, at least once the moment you can visualize in your plan in that beam arrangement, where will be the hot spot, where will be the cold spot, you can take care of it. There are beam modifying devices, there are techniques to take care of hot spot and cold spot. But if you are doing just trial and error here and there, it might work, not work, you would not know how many beams you will put, okay, on the planning system. So the hot spot, the cold spot, very simple. Now what to do? So you have to reduce wherever there's hot spot, you have to reduce the dose. Where there's cold spot, you have to increase the dose. It is all in relation to the dose in the center. So you put one wedge here. Wedge is thick end. Wherever there's a hot spot, the thick end has to be towards that side. Again, in exams, so often your students who are doing very well, everything is going top. Wedge, they have learned about wedge. Just draw a diagram. So just how will just draw your wedge on that. So sometimes they memorize the formula for deciding wedge angle. They will tell the wedge angle. I said no, but draw the direction of the wedge. Where will be the thick end, where there will be thin end. It could be only this side. Could be this side could be thick end, or it could be this side of the thick end. So they just so often it happens that the students just completely get wrong. Students who are otherwise going to get gold medal, they start sweating. Okay. So because they don't put wedges themselves, even they put wedges themselves, you don't sort of think about where the wedges should be. So the moment you have learned within 10 seconds of looking at a beam arrangement, in 10 seconds you should know in this beam arrangement, this is where I'll get hot spot, this is where I'll get cold spot. The moment you know that, You don't have to think even for a second. You will say, what a stupid question it is. Obviously, the thick end has to be here. Now you say, okay, on the other side. So people draw all kinds of things. So one side thick end here, and other field right lateral, they will put thick end here. What does it mean? So from here also, you see the maximum dose. So that's sometimes because you have not thought of. So you see in this voxel, both the fields are giving maximum. It is not just coming from one field. Why it has become more? Because both fields are giving more at that spot. So both sides, that beam has to be attenuated more. So obviously you put the right lateral wedge also in this thickened anterior. So it becomes a wedge pair. Sometimes you use a single wedge when you're using it only for a tissue compensation or something else like in breast and all, but generally it's a wedge pair. And you know that formula for deciding the wedge angle. You should know what is wedge angle. Okay, what is wedge angle? It's not the 50% isodose, but at a depth of say 10 centimeter, how much is the isodose line? Oh. Now, so anterior and lateral, right lateral fields were there. Now I have added a left lateral field. Okay. So again, it is very simple. You have just drawn that, flipped it. It's very straightforward. So this area is getting, in that hot 100 plus 100 of both and 60 from this right lateral. Okay. So as a result, if you see when you will combine, you write from individual how much it is getting in each box. Okay, you should do it as an exercise in each box. Just make it 6 or 8 voxel you write on each box. You will know. So otherwise, where will be the wedge? Wedge will be there or not? All the which field will be the wedge? First of all, whether there will be wedge or not, required or not. So that you just start thinking there will be a wedge. Okay. So if there will be a wedge in which field? That's the next question. Then what is the direction? So there are 3 steps where you can get it wrong. But if you can, so where will be the first? Again, as I said, it is a 20-second. You should get it. Where should be the hot spot? Where should be the cold spot? You have to think more. That means there's a fundamental flaw in your training or your thought process in terms of interaction. Now here it is interaction of beams. All throughout we have been reading about interaction of X-ray with matter. We have not read interaction of beam with beam. Okay. Remember when we say illumination in a hall. So how they say that this is illuminating. If suppose 2 strong lights are coming like this from this side, there will be a part which will get more illuminated. There will be part which will get less. Okay. So if you add it like this, if you see this is this area is getting 255, combining 95 plus 95 plus 65. 95 have kept both. So it is getting 95 from right lateral. It is getting 95 from the anterior beam and 65 from the left lateral. Okay. Then as it opened, but it will so happen in this area anteriorly, it will get high dose as a combined result of all the 3 beams together. Okay. Whereas this region, if you look at this region, from here it is getting very less only. So it is getting high dose only from anterior field. Okay, sorry, right lateral field. Okay, it is getting 95 from the right lateral field. Actually, I will make another one. I will give different colors to different beam, the numbers, different, so that it will be easy to understand. So it's getting 95 from there and 65, 65 from the other 2 beams. So it is getting only 225, 225, 225. So now once you have figured it out, what area is getting hot, what area is getting less hot, okay, or cold. The job is very simple. Okay, I'm sure all of you have figured out where to put the wedge. Which field the wedge? First and foremost, which field the wedge? Okay. So in 2 fields, because single wedge is very rarely used. So both the field now has 3 fields or 4 fields. So which field the wedge should be? So that also becomes easy, knowing where the field and the direction. So this is hot, this is cold. So wherever it is hot, there is thick end of the wedge. Wherever there is cold, this is the thin end of the wedge, and it's taken. Now, in practice, sometimes what is happening, because there is a missing tissue anteriorly. Okay, so what you are going to do, it is getting even hotter. There is a missing tissue. So I have not taken into account, that's why I have drawn a square. I have not shown into account the missing tissue or bone or etc. So I think I will just so now it is 4-field box. Anyone can guess it intuitively where will be the hot spot in a 4-field box? All over. 4 corners. Okay, so you think 4 corners. See, there are basically 5-6 beam arrangements you have to understand. Okay. So 4 corners. Anyone else feels 4 corners? Dekho, simple. Add it up. Because in any voxel, wherever it is more from right lateral, it is less from left lateral. Okay. Where it is more from anterior, it is less from posterior. So basically, these are 2 parallel opposed fields. Basically, a pair of parallel opposed fields. AP period right and left. And this we are presuming that the to keep it simple. So 4-field box is nothing by 2 parallel opposed fields, mediolateral and anteroposterior. And because they were giving a homogeneous dose distribution, nothing should change that. So you will find that everything. So if someone asks you, do you need a wedge pair for this? You would ask, why would you need a wedge pair? Here sometimes because there's a missing tissue anteriorly, suppose there's a missing tissue, because of that you're getting a hot spot, you might use 15-degree wedge, thick and anteriorly towards that you are using for as a missing tissue compensator. In the previous part, we were not using wedges as a missing tissue compensator. We were using wedges because of the field arrangement. The hot spot we were getting because of the field arrangement. Here, like in breast, we use wedges for as a missing tissue compensator, not because of the field arrangement. So hot areas are closest to both the fields and cold areas are farthest from both the fields. That is also, if there are beam arrangement, if it is like that, whichever is areas closest to both the beams, that will be hottest, which is farthest from this thing, that will be coldest. So other way, I've just put it simple, greater attenuation by thick end of the wedge this side and lesser attenuation, so you get a homogeneous dose distribution. And then you can, of course, calculate the hinge angle that you can calculate. So 90 minus hinge angle by 2, you will always get it. So 90-degree wedge pair, 90-degree hinge angle, which is anterolateral or posterolateral, but could be obliques also. It will be 90 minus 90 by 2, which will be 45. And after that, suppose the hinge angle is 120 degree, that is more, it is closer towards parallel opposed. Sometimes you get it, you forget this formula. Okay, it is very often anything which you have memorized, you are bound to forget. If not today, if not after 1 year, if not after 2 years, after 5 years, you will certainly forget. Okay, so how to remember this? So when will the effect become more pronounced? From 90-degree, when you become 120, you are almost making it parallel opposed. You are going towards making it parallel opposed. Okay, in parallel opposed, it is all homogeneous distribution. You don't need a wedge. Okay, whereas in from 90, when you are making it 60-degree, you are bringing it closer. You're going other way around. So there should be a greater hot spot. So you should require. So it was 45-degree for 90-degree. When it is 120-degree, then it is 30-degree, and when it is 60-degree, then it is 60-degree. Okay, so you just remember that from 90-degree, 120-degree is going towards parallel opposed. Parallel opposed is 180-degree. Okay, so so if suppose 120-degree hinge angle was there, so 90 minus hinge angle is 120 by 2, 60. Okay, so 90 minus 60 becomes 30-degree. And if the hinge angle is 60, okay, so like you're treating sometimes ear or parotid or sometime where there is, if you increase the hinge angle, it might go through the eye or spinal cord or somewhere else. You have used a narrow, less hinge angle. Then 90. Okay. So this is how you remember the need for wedges, which fields would require wedges, the direction of wedges, and the wedging. Okay. So this is a good way to remember. And mind you, this is because previously we had specific angles. Now, with the virtual wedges, it is not fixed that you should have only 45 or 30 or 60 degree. It could be 22 degrees, different kind of thing. Because patients are not square or rectangular, and there are other things also which are there. So that's why you can choose the wedge angle, but the guiding principle remains the same. So it doesn't matter. Sometimes you say, okay, two obliques, what will happen? But I have studied only anterolateral. You just go, it is still also like anterior. You just rotate it a little bit, it is like anterolateral. Okay. Just because you're thinking it is two obliques. I do not know about two obliques. Okay. This is rotated by it becomes anterolateral. Okay. So again, you have to see which way you have to put the field. Of course, patient bodies are not like boxes. Patients are not cardboard or this thing boxes, but roughly the same rule would apply. So the hinge angle, that formula of hinge angle and wedge angle would apply. So the same thing I have said. So this is 45 degrees. So these are the various kinds of field arrangement you could use. So I've shown here 120 degree, 60 degree. I have not shown. This is not 60. This is also not 60. I think I'll end it here, and I will share the link of the YouTube. This thing you all study that, watch that. I've explained in that this part and something else. Now I've shown an example of a skull, a tumor in the skull, inside the skull, a brain tumor, it's a frontal lobe tumor. It's a frontal lobe tumor. So first of all, and that treating with a isocentric technique, how many fields you have to use? If you're using multiple fields, where will be the hot spot and cold spot? Again, that you should get intuitively. The moment you decide for this, first of all, decide how many beams I use. Okay, what will be the beam arrangement? For that, you have to do principle, show no direction, this thing. And if I'm using this beam arrangement, where will be my hot spot? Where will be my cold spot? What I can do, okay, to use wedges, what will be the direction of my wedges? And then when we talk about simple 3D CRT, is there some place I can shield? Okay, so simple shielding, which beam I should use the shielding, which beam I should not use the shielding. So I've used the example of a frontal lobe tumor and the posterior part, in the PTV, the pituitary hypothalamic axis is coming. So that is all you'll see. It is just the concept of how to put field, how to modulate field. I'm talking of intensity modulated, which is also intensity modulation of the field, by the way. Okay, it is not modulating it voxel by voxel or not, this thing, but it is also modulating the intensity. When to use the shielding, that is also 3D CRT. When you can use a corner block. So a simple example for you all to conceptualize, understand how to do a simple 3D CRT. Anyone who has understood what is the principle of simple 3D CRT, rest everything is very easy. And if you have not understood a simple or a basic 3D CRT, you might say, we met this, that. The moment some planning system changes, they will change something, you will completely go for a toss. You would always want to be in a comfortable zone. Whatever technique is used, you will just know that, because beyond that, you don't understand. So, understanding of a simple, basic 3D CRT plan, how it is made, why you put that, what is shielded, what is not shielded, when you use wedges or when you don't use wedges, is most critical. And without that, you can never ever understand how radiotherapy treatment planning is done. You will always remain a contourer. You will contour something, you will write a prescription, they will make a plan. You all just see it is covered in 90%, 95%, this is okay. You will just sign it, accept it. Okay. The moment some challenge is coming, you will not be able to figure out for yourself what is there, or you will never be able to suggest a solution to your physicist. See, the patient physicist, we work as a team with physicists as radiation oncologist. So, like physicists, they will give you some input, you have to give some input. So that is very important. So I think we'll end for the day today. My God, I never thought it will go until 6:45. Okay, so tomorrow again a long day. We'll start at 9:30. Yeah, no, 10 o'clock, no, it is. Thankfully. Okay. I hope you all had a long day, but something good to take. And YouTube, I think people are still watching on YouTube. Okay. Everyone knows how to reach access. How many people from outside TMC? Can you raise your hand? Okay. I think tomorrow more people are coming. Many hospitals are working full day today, Saturday, no? So, and who all three of you are staying there at Harman? One, two, one more.